So, here's something that might settle differently once you hear it said out loud, here in the dark, with no particular need to do anything about it. Right now, as you lie there, the air easing into your lungs is doing something it has done since long before there were lungs to breathe it. Oxygen atoms, forged inside a star that died billions of years before our sun was even a faint possibility, are crossing a thin, wet membrane deep inside your chest. They are finding their way into your bloodstream, and there they are locking onto iron atoms, iron that was also forged inside a star, iron that has been drifting and gathering and reforming for longer than the Earth has existed. That meeting, oxygen touching iron inside you, is chemistry. It is not happening in a laboratory somewhere far away, under bright fluorescent lights and watched by people in white coats. It is happening in you, right now, in the quiet, in the dark, while you get ready to sleep. It is happening without your permission, without your attention, without any effort on your part at all. And that is the first thing worth holding on to tonight, not as a fact to memorize, but as a feeling to sit with. You are not a person who occasionally does chemistry, like you might occasionally cook a meal or take a vitamin. You are chemistry happening, all the time, whether you're watching or not. Tonight we're going to walk through all of chemistry, from the very beginning, the long human story of how we came to understand what things are made of, all the way through to how that understanding works right now, in your own body, in the room around you, in the air you just breathed in and will breathe out again in a moment. We're going to talk about what substances actually are, at the deepest level, why some things burn and some things rust, and some things just sit there quietly, unchanged, for 1,000 years. We're going to talk about why mixing certain things together makes something entirely new, something with properties neither of the original substances possessed on their own. By the end, you will understand the basic machinery underneath almost everything you can touch, breathe, eat, or see. Not the formulas, not the equations, the ideas, the actual shape of what's going on, the pattern underneath the pattern, the quiet logic that governs every material thing you have ever encountered. If that sounds like a lot, let it be a lot. There is no hurry. There is no test at the end of this. There is nothing you need to remember. If you fall asleep somewhere along the way, that is perfectly fine. That is in fact the whole point of this. Nothing here needs to be held on to. Nothing here needs to be memorized or recited back or even fully understood the first time through. The ideas will still be here if you want to come back to them later, waiting patiently, the way they have waited for thousands of years for anyone to notice them at all. And your body, in the meantime, will keep doing the chemistry it already knows how to do, all on its own, whether you're listening to a single word of this or not. Your lungs will keep exchanging oxygen for carbon dioxide. Your cells will keep breaking down the sugar from your last meal, carefully, gently, releasing just enough energy to keep you warm and keep your heart beating. Your enzymes will keep quietly speeding up the reactions that need to happen, millions of them, every second, inside every cell. None of that requires your attention. None of that requires you to be awake. It is all happening, right now, the same way it has been happening since before you were born, the same way it will keep happening tonight while you rest. To understand chemistry, you have to go back further than you might expect. Not to a laboratory, not to a scientist in a white coat. You have to go back to a fire, on a riverbank, tens of thousands of years ago, where someone noticed something strange happen to a lump of green rock that had rolled a little too close to the flames. The rock softened. It changed color. And when it cooled, it was no longer a rock at all. It was metal. That person, whoever they were, did not know what they had done. They had no words for it, no framework, no theory. But they had just performed one of the oldest chemical reactions humans ever learned to control, the smelting of copper ore. They had taken one substance and, through heat alone, turned it into something with entirely different properties, harder, shinier, useful in ways the original rock had never been. That moment, a person watching a rock become something else in the heat of a fire, is the seed of everything we are going to talk about tonight. Chemistry, at its root, is the study of what happens when one kind of matter becomes another kind of matter, and why. That's it. That's the whole thing. Underneath all the complexity, one kind of matter becoming another, and someone paying close enough attention to ask why. For a very long time, nobody asked why. They only asked how, and only well enough to repeat it. Early metalworkers in the regions we now call Turkey, Iran, and the Balkans figured out, through trial and a great deal of failure, how to get copper from stone, and later how to mix copper with tin to make bronze, a harder metal that held an edge and didn't bend under pressure. They didn't understand atoms or elements. They understood recipes. Add this, heat it this long, and you get this result. That is worth sitting with for a moment, because it tells you something important about how human knowledge actually grows. Chemistry as a craft, chemistry as something useful, existed for thousands of years before chemistry as an explanation existed at all. People made soap, made glass, made dyes, made medicines, long before anyone could explain in any satisfying way why any of those processes worked. They knew what worked. They had no idea why. And for a long time, that was enough. The first people we know of who tried to explain why matter behaves the way it does, rather than simply recording what worked and what didn't, were philosophers in ancient Greece, working around 2,500 years ago. A thinker named Thales, living in the city of Miletus, proposed something that sounds strange to us now, but was, in its own way, a genuinely bold idea. He said that everything in the world was, deep down, made of water, just in different forms. Rocks were water that had hardened, clouds were water that had expanded. Blood was water that had been heated and thickened by the body. It sounds odd to modern ears, but notice what he was doing. He was looking at the wild, chaotic variety of the world. Rocks, clouds, blood, wine, metal, wood, and trying to find one single underlying substance beneath all of it. That instinct, the idea that all of this complexity hides a simpler foundation, is the instinct that drives all of chemistry, even now. The details have changed. The instinct has not. A little later, another thinker named Empedocles refined this idea into something that would last, almost unchanged, for nearly 2,000 years. He proposed that everything was made of not one substance, but four: earth, water, air, and fire. Every object in the world, in his view, was some particular mixture of these four elements, combined in different proportions. A rock was mostly earth, with a little water to hold it together. Steam was mostly air and fire. Blood was a complicated mixture of all four, and that was why it flowed like water, but carried the warmth of fire. This idea, the four classical elements, became the accepted explanation for the nature of matter across the ancient Mediterranean world, and it was taught, more or less unchanged, all the way into the European Renaissance. It was wrong, as we now know, but it was wrong in a useful way, a way that gave people a framework for thinking about matter at all, and that is often how knowledge moves forward, one useful wrong idea at a time, each one slightly less wrong than the one before it. But there was another idea floating around at the same time, one that got much less attention for a very long time, and turned out, eventually, to be far closer to the truth. A philosopher named Democritus, working with his teacher Leucippus, proposed something genuinely radical. He said that if you kept cutting a piece of matter in half, again and again and again, you would eventually reach a point where you could not cut it anymore. A smallest possible piece. A fundamental unit that could not be divided further. He called this smallest piece atomos, meaning uncuttable. This is where our word atom comes from. Democritus believed that everything in the universe, absolutely everything, was made of these tiny, indivisible atoms, moving through empty space, differing from each other only in shape, size, and arrangement. Water atoms were smooth and round, which is why water flowed so easily. Earth atoms were rough and hooked together, which is why solid ground held its shape. It was a beautiful guess. It had almost no evidence behind it, and Democritus had no way to test it, no instrument that could see anything close to that small, no experiment that could settle the question one way or another. But it sat there, quietly, for 2,000 years, waiting for someone with better tools to come along and prove that he was right about the basic shape of the idea, even though he was wrong about almost every detail. The atoms were real. They were not smooth or rough or hooked together. They were something far stranger and more elegant, as we would eventually find out. But the core insight, that there is a smallest piece, a unit beyond which you cannot cut, that insight turned out to be true. For most of the next 2,000 years, though, it was the four-element theory that shaped how people thought about matter, and it fed directly into a strange and fascinating period of human history called alchemy. Alchemy began to take a more organized shape in the city of Alexandria, in Egypt, in the first few centuries after Democritus, where Greek philosophy blended with Egyptian metalworking traditions and Babylonian astrology. The alchemists of Alexandria were not simply mystics, though there were certainly mystics among them. Many of them were serious experimentalists, people who spent long hours building and refining equipment, testing procedures, recording what happened when they heated this or mixed that. They built early versions of stills and furnaces. They worked out ways to distill liquids, to separate mixtures, to purify metals. A great deal of the equipment and technique that would later become standard laboratory practice was invented during this period, by people whose stated goal was something we would now consider fantastical: the transformation of ordinary metals like lead into gold. This goal was not as foolish as it sounds today, if you remember what people believed at the time. If everything really was just earth, water, air, and fire, in different proportions, then in principle, changing the proportions should let you turn one substance into another. Lead and gold were both metals, both understood as combinations of the same basic elements, just mixed differently. Turning one into the other seemed, on paper, like a reasonable engineering problem, not a violation of nature. It never worked. But the tools invented while trying, distillation, sublimation, crystallization, the careful control of heat, those tools worked extremely well, and they are still used in chemistry labs today, essentially unchanged in principle. The alchemists failed at their stated goal, but they succeeded, without meaning to, at building the foundation of practical laboratory chemistry. This happens more often than you might think in the history of science. People aiming at one thing, missing it completely, and hitting something else, something that turns out to matter far more. Alchemy traveled from Alexandria into the Islamic world during what is often called the Islamic Golden Age, roughly the 8th through 13th centuries. This is where the story gets an important new character, a scholar named Jabir ibn Hayyan, who worked in the region that is now Iraq. Jabir did something that set him apart from most alchemists before him. He insisted on careful, repeatable experimentation, and he kept detailed records of what he did and what happened. He is credited with improving processes like crystallization and distillation, and with producing substances like nitric acid and sulfuric acid, which remain fundamental chemicals in laboratories to this day. The very word alchemy comes from the Arabic alchemia, and later, when European scholars stripped away the al, the word chemistry itself was born. Jabir also proposed his own refinement of the elemental theory, suggesting that metals were formed from combinations of mercury and sulfur in different ratios, an idea that, while still wrong in the details, represented real progress. It was a theory built specifically to explain the properties of metals, rather than borrowed wholesale from philosophy about the whole universe. It was a narrowing of focus, a willingness to say, let's not try to explain everything at once. Let's just try to explain this one category of things, and see where that leads. That willingness to narrow the question, to focus on one piece of the puzzle at a time, is one of the quiet habits of mind that separates modern science from the broader philosophical traditions that came before it. From the Islamic world, alchemical knowledge moved into medieval Europe, largely through Spain, where Arabic texts were translated into Latin. European alchemists spent the next several centuries chasing the same old goals, transforming base metals into gold, and searching for something called the philosopher's stone, a mythical substance believed to enable that transformation, and also, in some traditions, to grant eternal life. Kings funded alchemists, hoping to fill their treasuries with transmuted gold. Alchemists sometimes went to prison for fraud when their promised gold failed to appear, and it always failed to appear. And through all of this failure, generation after generation kept refining the actual techniques of the craft, kept building better furnaces, better glassware, better methods for purifying and separating substances. The goal was a fantasy. The byproducts were real, and they accumulated, slowly, over centuries, like sediment settling to the bottom of a river, building up a layer of practical knowledge that later scientists would draw on without always remembering where it came from. By the time you reach the 16 and 1700s, something important began to shift. A small number of people started to care less about turning lead into gold, and more about simply understanding what was happening when substances changed, for its own sake. They wanted to know, not to get rich, but because the question itself had become interesting to them. This shift, from alchemy chasing a goal to chemistry chasing an explanation, is the true beginning of the story you're going to hear the rest of tonight. It didn't happen on one particular day. It didn't happen with one particular experiment or one particular book. It happened slowly, as a handful of careful, stubborn people started asking a better question than the alchemists ever had. Not, how do I turn this into gold? But, what actually happens, at the deepest level, when one substance becomes another? And that question, once people started asking it properly, changed everything about how humans understood the material world they lived in. So if you're still drifting along with me, let yourself settle a little deeper now. Let the pillow take a little more of the weight. There's nothing you need to do with any of this. The story will keep unfolding, whether you're tracking every detail or not. The fire on the riverbank, the Greek philosophers guessing at atoms, the alchemists distilling and heating and hoping, all of it was just the long, slow prelude to a question that finally got asked clearly enough to be answered. And that answer, once it started to come into focus, turned out to be simpler and more elegant than anyone had guessed, and it explained, in the end, almost everything. We'll pick up that thread next, whenever you're ready, whenever your own quiet breathing tells you it's time to continue. The question that finally moved chemistry out of alchemy and into science was simple enough to ask, but it took nearly 100 years to answer properly. The question was this: when something burns, what is actually leaving it or entering it, and where does the weight go? This might not sound at first like the most gripping question anyone has ever asked, but think for a moment about what people were watching happen right in front of them all the time without understanding it. A log of wood, heavy and solid, burns in a fireplace and turns into a small pile of light gray ash, far lighter than the log it came from. Where did the rest of the wood go? It seemed to vanish, to disappear into the air, leaving almost nothing behind. And yet a metal like iron, left out in damp air, slowly grows a reddish crust, and as that crust thickens, the metal actually becomes heavier, not lighter. Where did that extra material come from? These two processes, burning and rusting, seemed completely different on the surface. One was fast and violent and left behind less material than you started with. The other was slow and quiet and left behind more. But a growing number of careful observers in the 16 and 1700s started to suspect that these two processes were secretly the same thing, just happening at different speeds. They were both somehow a reaction with the air itself, but nobody had yet figured out what that meant. The dominant explanation of the time was developed mainly by a German chemist named Georg Ernst Stahl in the early 1700s. He called it the phlogiston theory. Phlogiston, Stahl proposed, was a substance contained within all flammable and metallic materials, a kind of fire essence, an invisible something that lived inside things that could burn or rust. When something burned, he said, it was releasing its phlogiston into the air. A substance that had lost all its phlogiston was left as ash, or as what chemists called a calx, the crumbly residue left after a metal was heated strongly in open air. Rusting, in this view, was just a slower release of that same phlogiston. The theory explained a great deal, and for decades it was the accepted framework nearly everywhere in Europe. It made intuitive sense. Fire seemed to release something. You could feel the heat leaving. You could watch the material shrink and change. The idea that something was escaping felt right. But phlogiston theory had a serious problem, one that bothered careful experimenters for a long time before anyone dared to challenge the whole framework openly. If burning releases phlogiston, and phlogiston has weight, and something loses phlogiston when it burns, then the thing left behind, the ash or the calx, should weigh less than the original material. Wood ash did weigh less than wood. That fit perfectly, and it made everyone comfortable with the theory. But metals were a different story entirely. When you heated a metal like tin or lead in open air, the calx left behind consistently weighed more than the original metal, not less. Somehow, losing phlogiston was making the metal heavier. This was a genuine contradiction, and it nagged at people who paid close attention to their measurements. Some chemists tried to patch the theory by proposing that phlogiston had negative weight, that it actually made things lighter when it was present, so losing it would make the remaining material heavier. It was an awkward fix, a bandage over a wound that kept getting larger, and it did not sit well with the growing number of experimenters who insisted on actually weighing everything they did, carefully, before and after every experiment. This insistence on weighing things is one of the most important shifts in the entire history of chemistry, and it deserves real attention because it changed the nature of the whole field. Before this era, most natural philosophers described chemical changes in words, in qualities. Something became lighter or heavier, or changed color, or smelled different. But a small number of experimenters, working carefully with sealed containers and precise balances, began to insist on numbers. Exactly how much did this weigh before, and exactly how much does it weigh after? Not approximately, not roughly. Exactly. This shift, from qualitative description to quantitative measurement, is what allowed chemistry to become a real science rather than a collection of observations and folk recipes. You cannot find a hidden pattern in nature if you are not willing to measure carefully enough to notice when something doesn't add up. You cannot catch a contradiction if your numbers are vague. The phlogiston theory survived as long as it did partly because nobody was weighing the gases. Nobody was capturing what floated away. They were only weighing the solid leftovers, and the solid leftovers told a confusing story. But if you could weigh everything, the solids and the gases together, the whole story might change. One of the earliest and most important experiments along these lines was performed by an English clergyman and scientist named Joseph Priestley in the 1770s. Priestley was interested in the properties of different kinds of air, a subject that fascinated a whole generation of chemists at the time, because it was becoming increasingly clear that the air around us was not one single simple substance. It was itself a mixture of different things, different gases with different behaviors, and teasing those apart was one of the great scientific projects of the era. Priestley discovered that when he heated a red substance called mercury calx, using a large magnifying glass to focus sunlight onto it, it released a gas. And this gas was unlike ordinary air. A candle burned in it with a brighter, stronger flame than in ordinary air. A mouse placed in a sealed container with this gas remained lively and active far longer than a mouse in ordinary air. Priestley had produced oxygen, though he did not call it that, and did not fully understand what he had found. Working within the phlogiston framework he had inherited, he interpreted this new gas as air that had been stripped of its usual phlogiston, making it extra good at absorbing phlogiston from burning or breathing things, which was why fire and mice both thrived in it. He called it dephlogisticated air. He had the right observation, the right experiment, the right substance in his hands, but he was looking at it through the wrong lens, and the wrong lens kept him from seeing what he actually had. Priestley shared his finding with other scientists across Europe, as was the custom of the time, through letters and visits and long conversations over shared meals. And this is where the story turns to the person who would finally break the whole framework open. In 1774, Priestley met with a French chemist during a trip to Paris and told him about this gas he had produced. That chemist's name was Antoine Lavoisier, and what he did with Priestley's discovery over the following years would fundamentally rewrite the rules of chemistry. Lavoisier was, by nearly every account, an extraordinarily careful and rigorous experimenter, more concerned with precise measurement than almost anyone working before him. He had access to extremely accurate balances, some of the best instruments of the era, and he used them constantly, obsessively, the way a watchmaker might fuss over the tiniest gears. He weighed everything, before every reaction and after every reaction, in sealed vessels that prevented any gas from escaping unmeasured. This was a critical innovation, because earlier experimenters had often let gases simply drift away into the room, uncounted, unnoticed, which was exactly why phlogiston theory had been able to survive its own contradictions for so long. If you don't weigh the gas, you don't notice that it's the missing piece of the puzzle. You see the metal get heavier, and you scratch your head, but you never think to weigh the air around it, because the air seems like nothing, seems like empty space. Lavoisier understood that the air was not nothing, and that you had to account for it. Lavoisier repeated Priestley's mercury calx experiment, and many others like it, with this new level of rigor, and what he found tore the phlogiston theory apart. When metals were heated in a sealed container with a fixed amount of air, they gained weight as they formed a calx, and at the very same time, the air in the container lost a corresponding amount of weight. A portion of the air itself was consumed and disappeared, absorbed into the metal. It was not that phlogiston was leaving the metal, it was that something from the air was combining with the metal. Burning was not a release, it was a combination, an addition of a substance from the air into the burning material. The whole framework had been backward. Fire was not something leaving. Fire was something arriving, something joining, something binding itself to the material being burned. Lavoisier named this active portion of air oxygen, from Greek words meaning acid former, because he initially, and incorrectly, believed this gas was a necessary ingredient in every acid. He was wrong about that detail, but the core insight, that burning is a combination with a gas from the air, rather than a release of some fire essence, was correct, and it overturned nearly a century of accepted chemical theory in the span of a few short years. It was a complete reversal of how people thought about one of the most common processes in daily life. What Lavoisier had really found went deeper than oxygen alone. Buried inside his careful weighing was a principle that would become one of the true foundation stones of chemistry, a principle so fundamental that everything else in this science rests on top of it. He called it, in his own writing, something close to this idea. Nothing is created and nothing is destroyed in a chemical change. Matter only changes form. If you seal a reaction inside a container and weigh everything, the metal, the air, the gases produced, the total weight before the reaction, and the total weight after the reaction will always be exactly the same. This became known as the law of conservation of mass, and it is worth pausing on, because it is the single idea that makes chemistry a predictable, countable science, rather than a mysterious art. If matter cannot appear or disappear, only rearrange, then every chemical reaction is, at its heart, a bookkeeping problem. Everything that goes in must be accounted for in what comes out, just wearing a different shape, arranged into a different pattern, but never gone, never new, only reorganized. Let's slow down here and really sit with this idea, because it's going to matter for everything that follows. Imagine you have a box of building blocks, all different colors, all different shapes, and you build a small house out of them. Then you knock the house down and build a completely different structure, a little bridge, using the exact same blocks. The house is gone, the bridge is new, but you haven't gained or lost a single block. You've only rearranged what you already had. Chemical reactions work the same way. When wood burns, the wood does not vanish into nothing. Its atoms rearrange, combining with oxygen from the air to form new substances, mostly carbon dioxide gas and water vapor, both of which float away invisibly, along with a small residue of ash left behind, minerals that couldn't burn away. If you could somehow capture every single atom, the gases, the ash, everything, and weigh it all together, it would weigh exactly the same as the original wood plus the oxygen it consumed from the air. Nothing was lost. It just changed shape and mostly floated off where you couldn't see it. Which is exactly why, for thousands of years, it looked to everyone like weight was disappearing when things burned. The weight was leaving, but it was leaving as gas, as vapor, as something invisible, not as nothing. The mistake was not in the observation. The mistake was in not following the weight all the way to its new form. With this principle established, Lavoisier went further and did something equally important. He proposed a clear, testable definition for the word element, one that finally replaced the old four-element theory of earth, water, air, and fire, a theory that, by this point, had been quietly failing to explain actual experimental results for a long time. Lavoisier defined an element as a substance that could not be broken down into anything simpler through chemical means. If you could take a substance and split it into two or more different substances through a reaction, it was not an element. It was a compound, a combination of simpler things. If, no matter what you tried, you could never break a substance apart into anything else, only that same substance, then you were looking at a true element. Water, under this new definition, was immediately disqualified as an element. Using electricity, scientists could split water apart into two different gases, hydrogen and oxygen, and combine those two gases back together to reform water. Water was a compound, not an element. Air, too, failed the test, since it could be separated into oxygen, nitrogen, and other distinct gases. But oxygen itself and hydrogen and a metal like iron could not be broken down any further using any chemical technique available at the time. These were true elements, the actual basic building blocks of matter, the simplest substances from which everything else was built. Lavoisier published this new framework in 1789 in a book that laid out a complete list of the elements known at the time, along with a new, logical system for naming chemical substances based on what they were made of, rather than the confusing folk names that had accumulated over centuries, names like oil of vitriol or spirit of hartshorn, names that told you nothing about what the substance actually contained. This new naming system is, in its basic structure, still the one chemists use today. That same year, 1789, also happened to be the year the French Revolution began, and this detail matters for our story in a genuinely sorrowful way. Lavoisier, in addition to his scientific work, held a position collecting taxes for the French crown, a deeply unpopular role in a country growing increasingly angry at its rulers. When the revolutionary government came to power and began executing figures associated with the old regime, Lavoisier was arrested and, in 1794, put to death by guillotine. He was 50 years old at the height of his intellectual power, having just finished rewriting the foundations of an entire science. A mathematician of the time, upon hearing the news, is said to have remarked with real grief that it took the state only a moment to cut off that head, and that 100 years might not be enough to produce another one like it. It's a heavy thing to carry into a story about chemistry, but it's true, and it's worth knowing, because it's a reminder that the history of science is also always the history of actual human lives, lived inside actual difficult times, and that the people who move our understanding forward are never separate from the world they live in. Lavoisier's work gave chemistry two enormous gifts. It gave chemistry the law of conservation of mass, the idea that matter only rearranges and is never created or destroyed. And it gave chemistry a working, testable definition of an element. But there was still a missing piece, a question Lavoisier's framework did not answer. Why did elements combine in the particular proportions they did? Why, for example, did a certain fixed weight of hydrogen always combine with the exact same fixed weight of oxygen to make water? Every single time, in every single sample of water anywhere in the world, with no exceptions, and never any in-between amounts. This question would be answered by an English schoolteacher and amateur scientist working about 15 years after Lavoisier's death, a quiet, careful man named Dalton, whose patient attention to small patterns would open the next great chapter in the story. But that chapter can wait. For now, it's enough to rest with what Lavoisier gave us, the understanding that nothing is ever truly lost, only rearranged, and that the air itself is not empty, but full of substances waiting to combine, waiting to become part of something new. Lavoisier's work gave chemistry two enormous gifts. It gave chemistry the law of conservation of mass, the idea that matter only rearranges and is never created or destroyed. And it gave chemistry a working, testable definition of an element. But there was still a missing piece, a question Lavoisier's framework did not answer. Why did elements combine in the particular proportions they did? Why, for example, did a certain fixed weight of hydrogen always combine with the exact same fixed weight of oxygen to make water, every single time, in every single sample of water anywhere in the world, with no exceptions, and never any in-between amounts? This question would be answered by an English schoolteacher and amateur scientist working about 15 years after Lavoisier's death, a quiet, careful man named John Dalton. Dalton had spent years studying the behavior of gases and the weather, keeping meticulous daily records of atmospheric conditions for most of his adult life. This was not glamorous work. It was the kind of patient, daily attention to small things that rarely makes anyone famous. But it trained him, much like Lavoisier's obsessive weighing had trained him, to notice small, consistent patterns that other people might have overlooked. He was accustomed to watching for subtle regularities, for the way numbers repeated and proportions held steady, and around 1803, Dalton proposed something that revived Democritus's ancient guess about atoms, but did something Democritus never could. He gave it numbers. He gave the old guess a measurable shape. Dalton's proposal had several parts, and each one mattered enormously. First, he said, all matter is made of extremely small particles called atoms, which cannot be created, destroyed, or divided in ordinary chemical reactions. They are the basic units, the smallest pieces that still retain the identity of the substance they belong to. Second, all atoms of a given element are identical to one another in mass and properties, and atoms of different elements are different from one another. This was the crucial new idea, the thing Democritus had guessed but had no way to confirm. Every atom of hydrogen anywhere in the universe has the same weight as every other atom of hydrogen. Every atom of oxygen has its own different but also consistent weight. An atom of carbon carries its own characteristic heft, different from nitrogen, different from iron. This meant that elements were not just defined by their appearance or their behavior, but by something countable and fixed, something you could, in principle, weigh. Third, and this is the part that finally answered the question Lavoisier's work had left open, compounds form when atoms of different elements combine in simple, fixed, whole number ratios. Water isn't hydrogen and oxygen mixed in some random or variable proportion, a little more of this, a little less of that, depending on where the water came from. It is always, precisely, two atoms of hydrogen joined with one atom of oxygen, never 1.5, never 3. Always that same simple, fixed ratio, everywhere, every time, in every raindrop, in every ocean, in every glass of water poured anywhere on Earth. This gave chemists something they never had before, a reason for the exact numbers they kept measuring in the lab. If a certain weight of hydrogen always combined with exactly 8 times that weight of oxygen to form water, and never any amount in between, that consistency made total sense if water was always built from a fixed small number of hydrogen atoms bonded to a fixed small number of oxygen atoms, and each type of atom had its own unchanging weight. The numbers in the laboratory were not arbitrary. They were not mysterious. They were simply the consequence of counting atoms, one by one, in fixed groupings. Dalton went on to calculate the first table of relative atomic weights, comparing the weight of every known element's atom against the weight of a hydrogen atom, which he set as the baseline, the lightest of them all. Many of his specific numbers were later corrected as measurement techniques improved. He made mistakes. He didn't always get the ratios right. But the framework itself, atoms as the true, indivisible, countable units of chemistry, each element with its own characteristic weight, compounds as fixed combinations of these atoms in whole number ratios. This framework has never been overturned. Every advance in chemistry since 1803 has been built on top of Dalton's basic picture, refining it, adding enormous detail to it, but never replacing its central idea. Atoms are real, they are countable, and chemistry is, underneath everything else, the study of how these countable atoms combine, separate, and rearrange. It's worth pausing here to let that sink in, because it's one of those ideas that is easy to hear and nod along with, but harder to really feel the weight of. Every material thing you have ever encountered, every object, every liquid, every breath of air, every cell in your body, is built from a countable number of tiny, individual pieces, each one belonging to one of the basic types we call elements, each type with its own consistent weight, and those pieces combine in simple, predictable ratios to form everything else. The world is not a smooth, continuous blur of stuff. It is granular, it is particulate, it is made of distinct, separate units, and those units follow rules that we can write down and count. That is what Dalton gave us. Not just a theory, but a way of seeing the material world as something countable, something that adds up, something where the numbers always have to balance. Dalton's atomic theory gave chemistry its basic units, but it left the field with a growing, messy pile of individual facts. By the middle of the 1800s, chemists had identified more than 60 different elements, each with its own atomic weight, its own melting point, its own tendency to react or not react with other substances. It was a little like being handed 60 different puzzle pieces with no picture on the box to guide you. Some elements clearly behaved similarly to others. Lithium, sodium, and potassium, for instance, were all soft, silvery metals that reacted violently, almost explosively, when dropped into water. Chlorine, bromine, and iodine were all sharp-smelling, reactive substances that liked to grab onto metals to form salts. But nobody had found the deeper reason why these particular groupings of elements shared their behavior. It looked like a pattern, it smelled like a pattern, but nobody could yet explain the pattern, or predict where it would lead, or say with confidence what element should come next. Before we get to the person who finally organized this pile of elements into real order, it's worth mentioning an Italian scientist named Amedeo Avogadro, who in 1811 proposed an idea that took decades to be properly accepted, but turned out to be essential. Avogadro suggested that equal volumes of different gases, at the same temperature and pressure, contain equal numbers of particles, regardless of what the gas actually is. This sounds like a small, technical detail, a footnote in a larger story, but it solved a serious confusion that had been holding chemistry back. Chemists at the time had been mixing up two different ideas: the atom, the smallest possible piece of an element, and what we now call the molecule, a group of atoms bonded together that behaves as a single independent unit. Avogadro's insight helped clarify that a gas like oxygen doesn't float around as lone single atoms, but as pairs, two oxygen atoms bonded together into one molecule, and that this distinction mattered enormously for getting atomic weights correct. If you thought an oxygen atom was floating around alone, you would calculate its weight one way. If you understood it was actually a pair of atoms traveling together, you would calculate it differently, and more accurately. It took the chemistry community until roughly the 1860s to fully accept and apply Avogadro's idea, largely due to the efforts of an Italian chemist named Stanislao Canizzaro, who presented a clear, systematic argument for it at a major chemistry conference in Germany in 1860. But once it was accepted, atomic weights across the field were finally standardized and corrected, which mattered enormously for what came next, because you cannot find an order in your data if your basic numbers are still wrong. You cannot see the pattern if the numbers you're arranging are off by a factor of 2. With more reliable atomic weights in hand, a Russian chemistry professor named Dmitry Mendeleev sat down in 1869 to work on a textbook. He was trying to find a sensible way to organize and teach his students about the growing list of known elements, and the problem was genuinely difficult. The elements were piling up, each with its own personality, its own quirks, and there was no obvious way to present them that didn't feel like an arbitrary list. Mendeleev is said to have written each element's name, atomic weight, and known properties onto its own individual card, then spent long hours arranging and rearranging these cards, searching for an order that made sense, much like a person laying out a complicated hand of solitaire, trying to find the arrangement that clicked. And he found one. When he arranged the elements in order of increasing atomic weight, a pattern emerged, clear and unmistakable. Certain properties repeated at regular intervals. Every eighth element, roughly, shared strong similarities with the one before it, forming natural columns when the cards were arranged into a grid. Soft reactive metals like lithium, sodium, and potassium lined up neatly beneath one another. Sharp reactive nonmetals like fluorine, chlorine, and bromine lined up in their own separate column. This repeating pattern is why the arrangement became known as the periodic table. Periodic meaning something that repeats at regular intervals, the same word used to describe the tides or the phases of the moon, anything that comes back around in a predictable rhythm. What made Mendeleev's version of this idea genuinely brilliant, rather than merely observant, was his willingness to trust the pattern even when the existing data seemed to argue against it. When he found gaps in his grid, places where an element should exist to complete a pattern but no known element fit, he did not force a known element awkwardly into the wrong slot just to fill the hole. He didn't fudge the data, he didn't pretend the pattern was tidier than it was. Instead, he left the space empty, and he made a bold declaration. He said an undiscovered element must exist to fill this gap, and he predicted, in advance, its approximate atomic weight and its likely properties, based purely on the pattern surrounding the empty space. He looked at the elements above and below the gap, looked at the elements to the left and right, and he said, "Something belongs here, something we haven't found yet, and it will have roughly this weight, roughly this density, roughly this melting behavior." This was a profound act of confidence in an underlying order that nobody could yet fully explain. Mendeleev didn't know why the pattern existed. He simply trusted that it was real, and that reality would eventually catch up to fill in the blanks he had left on purpose. Reality did catch up, and it did so with a swiftness that must have been deeply satisfying. In 1875, a French chemist found a new element through careful analysis of a zinc ore, and he named it gallium. Its properties matched almost exactly what Mendeleev had predicted years earlier for a gap he had labeled eka aluminum, right down to its density and its melting behavior. A few years later, a similar story played out with an element named scandium, which matched his predicted Enica boron, and again with an element named germanium in 1886, which matched his predicted eka silicon so closely that it became one of the most celebrated confirmations in the history of chemistry. Imagine predicting the exact weight and behavior of a substance nobody has ever seen, based only on the empty space it should occupy in a grid, and then watching someone find that exact substance years later, in a mine, in a mineral sample, exactly where the pattern said it should be. That is the kind of moment that transforms a clever organizational trick into a real scientific law. Something that reveals a genuine hidden structure in nature, rather than just a convenient way of sorting information. The periodic table was not just a chart on a classroom wall. It was a map of something real, something deep, something built into the fabric of matter itself. Still, a real mystery remained underneath all of this success, one that would not be solved for several more decades. Why did this pattern exist at all? Why should every eighth or so element share properties with the ones before it? Mendeleev had organized the elements by atomic weight, and the pattern worked well enough to make astonishing predictions, but weight alone didn't explain why the repetition happened, or why it happened at those particular intervals. There were even a few troubling exceptions, pairs of elements, like tellurium and iodine, where the heavier element had to be placed before the lighter one in the grid to preserve the pattern of properties, which made no sense if atomic weight was truly the fundamental organizing principle. Something deeper than weight had to be going on, some hidden property of the atom itself that weight merely tracked along with, most of the time, but not perfectly, not in every case. Answering that question would require looking inside the atom itself, something nobody in Mendeleev's era had any way to do. That would have to wait for an entirely new set of experiments and ideas, ones that would show that the atom, which Dalton had described as an uncuttable, indivisible unit, was in fact built out of even smaller pieces, and that it was the identity and arrangement of those smaller pieces that truly determined everything about how an element behaves. The answer was not in the weight of the whole atom. The answer was in its structure, its inner architecture, the way it was put together from parts that nobody in Mendeleev's time even suspected existed. But that part of the story comes later. For now, as you lie there in the dark, it's enough to rest with what Mendeleev's table represents. It represents the idea that the chaos of the material world, the wild variety of substances and colors and textures and behaviors, is not chaos at all. It is a pattern, a repeating rhythm, a structure that reveals itself when you line things up in the right order and pay close enough attention. The elements are not a random assortment. They are a family, with relationships and resemblances and predictable gaps where a missing member should sit. And that idea, that deep order beneath apparent disorder, is one of the quiet comforts that chemistry offers. The world is not arbitrary. It follows rules. And those rules are knowable, countable, mappable onto a grid that fits on a single sheet of paper. Every element that makes up your body, every atom in the air you're breathing right now, has its own place on that grid, its own relationship to every other element, its own role in the slow, repeating dance that matter has been doing since the first atoms formed. If you're still with me, let your eyes close now if they aren't already. You don't need to follow every word from here. Just let it wash over you. The explanation continues either way, and there is nothing you need to hold on to, nothing you need to remember. It will still make sense later, whether you catch all of it tonight or not. So let's go inside the atom itself, gently, the way you'd walk into a quiet room you've never seen before. For most of the 1800s, the atom was treated as a solid, uncuttable little sphere, exactly as Dalton had described it. It was a tiny, hard marble, the smallest possible piece of any element, and that was the end of the story. But right around the turn of the 20th century, a series of careful experiments revealed that the atom was not solid at all. It was mostly empty space, built from smaller pieces, and understanding those pieces would finally explain why Mendeleev's pattern existed, why the periodic table worked the way it did, why elements fell into those repeating columns and rows that he had mapped out on his cards. The first piece was found by an English physicist named J.J. Thomson in 1897, while studying the strange glowing beams that appeared inside sealed glass tubes when electricity passed through them. These beams were faint and eerie, a kind of greenish glow that moved when a magnet was brought near. Thomson determined that these beams were made of tiny particles, far lighter than any atom, carrying a negative electric charge. He called them electrons. This was a genuinely strange finding, because it meant the atom, thought to be the smallest possible piece of matter, the uncuttable thing Democritus had named and Dalton had counted, was itself made of even smaller pieces. The atom was not the bottom, there was something beneath it. Thomson proposed a model where these negative electrons were scattered through a positively charged substance, a bit like raisins studded through a soft pudding, and this became known, somewhat playfully, as the plum pudding model. The atom, in this picture, was a soft, positively charged blob, with little negative dots scattered through it, like seeds in a fruit, like chips in a cookie. The plum pudding model did not last long. It was a reasonable guess, but guesses in science have to face experiments, and the experiment that came next changed the picture entirely. In 1911, a New Zealand-born physicist named Ernest Rutherford, working with a team in England, ran an experiment that was elegant in its simplicity. Rutherford's team fired a stream of tiny positively charged particles, called alpha particles, at an extremely thin sheet of gold foil, only a few atoms thick. They expected the particles to pass through with only slight deflection, since the plum pudding model predicted that positive charge was spread out evenly and thinly through the atom, like a fog, offering little resistance. A bullet fired through fog doesn't bounce back. It keeps going, maybe nudged a little to one side. That was what they expected. Most of the particles did pass straight through, just as expected, but a small number, roughly 1 in 8,000, bounced almost straight back, as if they had struck something dense and solid, something hard and massive buried inside the atom. Rutherford described this result as being about as believable as firing a large artillery shell at a piece of tissue paper and having it bounce back and hit you. It made no sense under the plum pudding model. The only explanation that fit was that the positive charge of the atom and nearly all of its mass was concentrated in an incredibly tiny, dense region at the very center, a region Rutherford named the nucleus. The electrons, by comparison, occupied a vast, mostly empty space surrounding this nucleus. If an atom were expanded to the size of a large sports stadium, the nucleus at its center would be roughly the size of a single pea sitting in the middle of the field. Everything else would be empty space, with the electrons like tiny specks of dust orbiting far away in the upper seats. Nearly everything about the physical size of matter, the reason a rock feels solid, the reason your hand cannot pass through a table, comes down to electron behavior in that vast outer space, not to the tiny dense nucleus itself. The solidity of the world is not because atoms are packed tightly like marbles in a jar. It's because the electron clouds of neighboring atoms push against each other, resisting overlap, creating the sensation of solidness out of mostly empty space. A few years later, the nucleus itself was found to contain two kinds of particles. Positively charged particles called protons, first clearly identified by Rutherford himself, and, found later in 1932 by an English physicist named James Chadwick, particles with no electric charge at all, called neutrons. This gives us the complete basic picture of the atom that chemistry still uses today. A tiny, dense nucleus at the center, containing protons and neutrons packed tightly together, surrounded by a much larger cloud of electrons. The number of protons in the nucleus is the single most important number in all of chemistry, because it is this number, and only this number, that determines which element an atom is. 1 proton makes an atom hydrogen, no matter how many neutrons or electrons happen to be present. 6 protons makes it carbon. 8 protons makes it oxygen. 79 protons makes it gold. Change the number of protons, and you change the identity of the element itself. It's that simple. It's that fundamental. This is, at last, the deep reason behind Mendeleev's pattern. He had organized elements by atomic weight, which mostly tracks proton count, but not perfectly, since weight is also affected by neutrons, which add mass, but don't change the element's identity. The truer, cleaner organizing principle, found decades after Mendeleev's death through further research into atomic structure, is proton count, now called the atomic number. When elements are arranged strictly by atomic number rather than raw weight, every one of the old troubling exceptions, like tellurium and iodine, falls neatly into place, and the pattern becomes perfectly consistent. Tellurium is heavier than iodine, but it has fewer protons, so it belongs earlier in the table. The weight was a distraction, a clue that mostly worked but sometimes misled. The true organizing principle was the number of protons, the atomic number, the thing that gives an element its chemical identity. But why does the pattern repeat every 8 elements or so in the first place? Why do elements with 1 proton, then 9 protons, then 17 protons, all behave similarly? The answer lies in how electrons are arranged around the nucleus, and this is one of the more elegant ideas in all of science, so let's take it slowly. Electrons do not simply swarm randomly around the nucleus. They occupy specific regions of space, often called shells, or more precisely, energy levels, arranged like layers around the nucleus, similar to the layers of an onion, though the comparison isn't perfect, because unlike onion layers, these regions have specific, limited capacities. They can hold a certain number of electrons and no more. The shell closest to the nucleus can hold a maximum of 2 electrons and no more. The next shell out can hold a maximum of 8. The shell after that can also hold 8, in the simple picture we're using tonight, before a new layer of complexity begins. Electrons fill these shells starting from the innermost one outward, the way water fills a glass from the bottom up. The first shell gets its 2, then the next shell starts filling, 1 electron at a time, until it reaches 8, and so on outward. Here is why this matters so much for chemistry. Atoms are, in a very real sense, always trying to reach a stable, settled arrangement, and it turns out that having a completely full outer shell of electrons is an extremely stable, low-energy, comfortable state for an atom to be in. An atom with a full outer shell tends to be calm, content, and unreactive. It doesn't want to gain electrons, and it doesn't want to lose them. It is, in a chemical sense, satisfied. This is exactly why a small group of elements called the noble gases, helium, neon, argon, and their relatives, are famously unreactive, almost never combining with anything else. Their outer electron shells are already completely full. Helium has its outer shell full with just 2 electrons, since it only has that innermost shell. Neon has its outer shell full with 8. Argon has its outer shell full with 8. They have nothing to gain and nothing to lose, so they simply drift through the world, chemically speaking, alone and undisturbed. They don't form bonds. They don't make molecules. They just exist, complete in themselves. Almost every other element, though, has an outer shell that is not full, and this incompleteness is the entire engine behind chemical reactions. An atom with an incomplete outer shell is, in a sense, restless. It wants to become stable, the way that full outer shell would make it. It wants to reach that settled, satisfied state. And there are really only 3 basic strategies an atom can use to get there, and every single chemical bond in the universe, every material you have ever touched, is built from one of these 3 strategies. Every substance, every molecule, every solid object in your life is the result of atoms trying to fill their outer shells, trying to reach that state of calm completion that the noble gases already have. The first strategy is to simply give away extra electrons. Sodium, for example, has 1 lone electron sitting by itself in an otherwise empty outer shell. It has 2 electrons in its first shell, 8 in its second, and then just 1 in its third. Rather than try to find 7 more electrons to fill that third shell completely, which would take a great deal of energy, it's far easier for sodium to just get rid of that 1 lone electron entirely, leaving the shell beneath it, which is already full, as its new outer shell. When sodium loses that electron, it becomes a sodium ion, and because it has lost a negatively charged electron while keeping all its positively charged protons, it now carries an overall positive charge. It has become satisfied by giving something away. The second strategy is the mirror image of the first. Rather than giving electrons away, an atom can grab extra electrons to fill up its outer shell completely. Chlorine, for example, has 7 electrons in its outer shell, just 1 short of the full set of 8. It is so close to being complete. Rather than giving away all 7, which would take enormous energy, it's far easier for chlorine to simply grab 1 more electron from somewhere else, completing its shell. When chlorine gains that extra electron, it becomes a chlorine ion, carrying an overall negative charge, since it now has 1 more electron than it has protons. It has become satisfied by taking something in. Now here is where the real elegance appears. Put sodium and chlorine together, and something almost inevitable happens. Sodium wants to give away exactly 1 electron. Chlorine wants to receive exactly 1 electron. They are, in a chemical sense, made for each other. So sodium simply hands its lone outer electron directly to chlorine. Sodium becomes a positively charged ion. Chlorine becomes a negatively charged ion. And because opposite electric charges attract one another strongly, these 2 ions snap together and hold on tight. This is called an ionic bond, a bond formed through the complete transfer of electrons from one atom to another, held together afterward purely by the electrical attraction between the resulting charges. The substance formed this way is sodium chloride, which you know far better by its everyday name, ordinary table salt. Every grain of salt on your kitchen counter is an enormous, orderly, repeating lattice of sodium and chlorine ions, stacked together in a precise three-dimensional grid, held together by nothing more than the simple electrical attraction between a positive charge and a negative charge, repeated over and over, trillions upon trillions of times, in every visible grain. The whole structure is just that one idea: give and take, positive and negative, repeated endlessly into something you can hold in your hand. The third strategy is different from the first two, and it's arguably even more important, because it's the strategy behind the vast majority of the molecules that make up living things, including you. Instead of one atom completely giving an electron away and another atom completely taking it, two atoms can instead choose to share a pair of electrons between them, with both atoms counting that shared pair as part of their own outer shell at the same time. This is called a covalent bond. Think of it less like a gift, and more like two people holding a single umbrella together in the rain, both benefiting from it, neither one fully possessing it alone. They both need it. They both use it. It belongs to both of them at once. Hydrogen provides the simplest possible example. A single hydrogen atom has just one electron in its outer shell, but that shell needs two electrons to be considered full, since hydrogen's shell is the smallest kind, the one that only holds two. Two hydrogen atoms can solve this problem together by sharing their two electrons between them, each atom now getting to count both electrons as satisfying its own need for a full shell. This is why hydrogen gas in nature is never found as lone single atoms floating around, but always as pairs of hydrogen atoms bonded tightly together, sharing their electrons, forming what's called a hydrogen molecule. Water gives us a slightly larger and even more important example of covalent bonding. Oxygen has 6 electrons in its outer shell, 2 short of the full set of 8 it needs. Rather than grabbing 2 electrons outright the way chlorine does, oxygen instead forms 2 separate covalent bonds, sharing one pair of electrons with one hydrogen atom and another pair of electrons with a second hydrogen atom. Each hydrogen atom gets to count its shared pair as completing its own small shell, and oxygen gets to count both shared pairs as helping complete its own larger shell. The result is a single water molecule, one oxygen atom bonded to 2 hydrogen atoms, exactly the 2-to-1 ratio that Dalton had puzzled out from careful weighing measurements. More than a century before anyone could explain why that particular ratio was the one nature always chose. The reason was sitting quietly inside the electron shells the whole time, waiting for someone to look closely enough to find it. Oxygen needs 2 more electrons. Each hydrogen can share one, so 2 hydrogens bond to 1 oxygen. The arithmetic of the outer shells dictates the shape of the molecule. There's a fourth kind of bonding worth mentioning briefly here as well, because it explains something you interact with constantly, though it doesn't fit neatly into the giving, taking, or sharing picture in quite the same way. Metals like iron, copper, and gold bond to one another through what's called metallic bonding, where the outer electrons of every atom in the material are not tied to any particular pair of neighboring atoms at all, but instead flow freely throughout the entire structure, like a shared sea of electrons drifting among a fixed lattice of positively charged metal atoms. This freely flowing sea of electrons is exactly why metals conduct electricity so well, since electric current is, at its heart, simply electrons moving through a material, and why metals can be hammered and bent into new shapes without shattering, since the positive atoms can slide past one another while remaining bathed in that same shared electron sea, never fully losing their grip on it. The electrons are not locked into place. They are mobile, communal, a shared resource that gives metals their characteristic flexibility and shine. Once you understand these few basic bonding strategies, giving electrons away, taking electrons, sharing electrons, and the shared electron sea of metals, an enormous portion of the material world starts to make sense in a new way. A chemical reaction at its core is simply the breaking of some existing bonds between atoms, followed by the forming of new, different bonds between a rearranged set of atoms, exactly matching the picture Lavoisier had glimpsed with his careful balances, but now with a clear physical explanation for why matter rearranges the way it does, and why it settles into the particular stable combinations it settles into, and not into others. Every bond that breaks either releases energy or requires energy to break, and every new bond that forms either releases energy or requires energy to form, which is exactly why some reactions release heat, like burning wood, while others absorb heat from their surroundings, like the cooling sensation of certain substances dissolving in water. The overall balance between the energy needed to break old bonds and the energy released by forming new ones determines whether a reaction feels hot or cold, fast or slow, and whether it happens easily on its own or needs a push of outside energy, like the spark from a match, to get started at all. All of it, all the variety of chemical change in the world, comes down to electrons rearranging themselves into more stable patterns, seeking that full outer shell, that settled state, that quiet completion. With that foundation in place, we can now walk through the different branches and variations that grow out of these basic ideas, the different shapes that chemistry takes once you start applying these same simple rules to different situations. The core logic doesn't change. Electrons still seek stable arrangements. Atoms still give, take, and share. But the way those simple strategies play out across different conditions, different temperatures, different combinations of elements, produces a richness and variety that can fill a lifetime of study. Tonight, we'll just trace the outlines, the broad contours, enough to recognize the patterns when you encounter them in your own daily life. Let's start with something you experience every single day, without necessarily thinking of it as chemistry: the states of matter. Solid, liquid, and gas are not different substances. They are not different kinds of material in any fundamental sense. They are different arrangements of the exact same particles, differing only in how tightly those particles are held together and how much energy they have to move around. The particles themselves, the atoms and molecules, remain exactly what they were. Nothing about their identity changes. Only their relationships to one another shift. In a solid, atoms or molecules are locked into fixed positions relative to one another. They are not frozen absolutely still. They vibrate, they jitter in place, they have a certain amount of energy that keeps them trembling, but they cannot travel, they cannot slide past their neighbors. Each particle stays in its assigned spot, held there by the bonds or attractions between it and the particles around it, which is why a solid holds a firm shape all on its own. You can set a rock on a table and it stays a rock. It doesn't spread out, doesn't flow, doesn't rearrange itself to match the container. The particles inside it are locked in formation, a tiny frozen crowd, each member vibrating but none of them leaving their place. In a liquid, the particles have enough energy to slide past one another freely. They are still close together, still touching, still interacting, but they are no longer fixed in position. The bonds between them are constantly breaking and reforming, a fluid dance of temporary connections. This is why a liquid flows and takes the shape of whatever container holds it while still remaining fairly close together overall, unable to easily separate from one another. Pour water into a bowl and it spreads out to fill the bowl. Pour it into a tall glass and it rises up the sides. The molecules adjust, slide, accommodate, but they stay together as a group, a loose community rather than a rigid formation. In a gas, the particles have enough energy to break away from each other almost entirely. They fly around independently and spread out to fill whatever space is available to them, with huge amounts of empty space between individual particles. A gas molecule in the air you're breathing right now is mostly alone, traveling through emptiness, only occasionally bumping into another molecule before bouncing away again. The space between gas particles is vast compared to the particles themselves, which is why gases are so light, so compressible, so easy to expand and contract. Adding heat energy to a substance gives its particles more energy to move, which is why ice melts into water and water boils into steam as you add heat. The heat doesn't change what the molecules are. It just gives them more motion, more freedom, more ability to overcome the attractions that hold them together. Removing heat energy takes that motion away, which is why steam condenses back into water and water freezes back into ice as it cools. The particles slow down, their mutual attractions reassert themselves, and they settle back into a more orderly, less mobile arrangement. The chemical identity never changes through any of this. A molecule of water is still exactly the same molecule, two hydrogens covalently bonded to one oxygen, whether it's frozen solid in an ice cube, flowing as liquid in a glass, or floating invisibly as vapor in the air above your cup of tea. Only the arrangement and energy of the molecules changes, not the molecules themselves. The water in your breath, the water in your tears, the water frozen in a glacier on a distant mountain, it's all the same substance, just in different states, different levels of energy and freedom. Now let's talk about acids and bases, a pairing you've probably heard mentioned before, without necessarily knowing what the words really mean. The terms float around in everyday life, in cleaning products, in discussions of food and health, but the underlying idea is simple and elegant. An acid, in the simplest useful definition, is a substance that releases hydrogen ions when dissolved in water. A hydrogen ion is just a hydrogen atom that has lost its one electron, leaving behind a lone positively charged proton, a tiny particle of pure positive charge swimming free in the solution. A base is, roughly, the opposite, a substance that either releases hydroxide ions, which are oxygen and hydrogen bound together carrying a negative charge, or otherwise soaks up those free hydrogen ions from the surrounding solution, reducing their concentration. This tug-of-war between substances that release positive hydrogen ions and substances that absorb them is what gives us the whole concept of pH, a numerical scale describing how acidic or basic a solution is. The scale runs from 0, extremely acidic, up through 7, perfectly neutral, like pure water, up to 14, extremely basic. Each step on the scale represents a tenfold change in the concentration of hydrogen ions, so a solution with a pH of 3 has 10 times as many free hydrogen ions as a solution with a pH of 4. It's a logarithmic scale, which means small changes in the number represent large changes in the actual chemistry. Lemon juice sits down around pH 2, quite acidic thanks to the citric acid the lemon produces. Your blood sits in an extremely narrow, carefully regulated range, right around pH 7.4, just slightly basic, and your body works constantly, through breathing and kidney function, to keep it locked precisely there, because even small deviations from that narrow range can be dangerous. If your blood pH shifts by more than a few tenths of a point in either direction, serious consequences follow. Proteins change shape, enzymes stop working, the careful balance of your internal chemistry begins to unravel. Your body monitors and adjusts this balance every moment. Without your awareness, maintaining a chemical environment of extraordinary precision. When an acid and a base are mixed together in just the right proportions, they neutralize each other. The acid's free hydrogen ions and the base's hydroxide ions combine to form perfectly neutral water, H plus OH giving H2O, while whatever ions are left over settle into a salt. This salt is the exact same kind of ionic compound we talked about with sodium and chlorine a little while ago, just formed through a different starting pathway. If you mix hydrochloric acid with sodium hydroxide, you get water and sodium chloride, ordinary table salt, the same substance that sits on your kitchen counter, born here from the meeting of opposites, the cancellation of acidic and basic extremes into something stable and neutral. Chemists also divide their field into two enormous, sprawling territories, called organic chemistry and inorganic chemistry, and the distinction, though it sounds like it should be about living versus non-living material, is actually simpler and a little more specific than that. Organic chemistry is, essentially, the chemistry of carbon, specifically carbon compounds that also typically contain hydrogen. This might sound like an oddly narrow definition for such a huge branch of the field, a whole discipline built around a single element. But carbon has a property that is almost unique among all the elements, a property that justifies the enormous attention it receives. Carbon has exactly 4 electrons in its outer shell, out of the 8 needed to be full, which means it can form 4 separate covalent bonds at once, sharing electron pairs with up to 4 different neighboring atoms simultaneously. And crucially, carbon atoms bond extremely well with other carbon atoms, chaining together into long strands, branching structures, and closed rings, almost like an endlessly reconfigurable set of building blocks. Carbon can link to carbon, which can link to more carbon, building skeletons of almost any length and shape, each carbon still having bonds free to connect to other elements like hydrogen, oxygen, and nitrogen. This single property, carbon's ability to link with itself in long, stable chains while still having bonds free to connect to other elements, is the entire reason carbon-based chemistry became complex enough to build living things. No other element forms such long, stable, versatile chains. Silicon, carbon's closest relative on the periodic table, can form chains, but they are less stable and less varied. Carbon is uniquely suited to be the backbone of complex molecules. The molecules that make up your muscles, your DNA, the sugar in your bloodstream, the fat stored in your body, all of it is built from long carbon chains and carbon rings, decorated with other atoms hanging off the sides. The architecture of life is carbon architecture, a vast branching tree of linked carbon atoms with hydrogen, oxygen, nitrogen, and other elements attached at specific points, like ornaments on a framework. Inorganic chemistry, by contrast, covers essentially everything else: the chemistry of metals, minerals, salts, and the compounds of elements other than the specific carbon-hydrogen combinations that define the organic realm. Though there are always a few historical exceptions and edge cases that don't fit neatly into either box, as tends to happen with categories humans invent to organize a messy natural world. It's worth spending a little time now on the different basic patterns that chemical reactions tend to follow, because once you see these patterns, you start to notice them everywhere. They become familiar shapes, recurring motifs in the endless dance of atoms. A synthesis reaction is the simplest pattern where 2 or more simpler substances combine to form one larger, more complex substance, the way hydrogen and oxygen combine to form water. 2 become 1. The parts join to make a whole that is different from either part alone. A decomposition reaction runs the opposite direction, a single complex substance breaking apart into 2 or more simpler substances, often triggered by heat or electricity, the way water can be split back apart into hydrogen and oxygen gas using an electric current, in a process called electrolysis. 1 becomes 2. The whole splits back into its original parts, like a building being carefully dismantled back into individual bricks. A displacement reaction happens when one element swaps places with another element already bonded inside a compound. It's a kind of chemical substitution, a trade. A piece of iron dropped into a solution containing copper ions will cause the iron to dissolve and the copper to plate out as solid metal, because iron holds onto electrons less tightly than copper does and effectively takes copper's spot in the arrangement. The iron goes into solution, becoming iron ions, and the copper comes out of solution, becoming solid copper metal. It's a swap, a transfer, one element stepping in and another stepping out. And then there are combustion reactions, the fast, heat-releasing reactions we touched on earlier with Lavoisier, where a substance combines rapidly with oxygen, releasing a burst of energy as new, more stable bonds form, faster than the surrounding material can absorb and dissipate that heat gently, which is why combustion tends to produce visible flame and light rather than just gentle warmth. The energy released by the new bonds forming exceeds the energy needed to break the old bonds, and the surplus pours out as heat and light, sometimes gently, sometimes violently. Sitting underneath many of these reaction types is one more idea worth understanding clearly, because it connects directly back to those electron strategies we just walked through, oxidation and reduction, often just called redox reactions. When Lavoisier found that metals gain weight by combining with oxygen from the air, he had actually stumbled onto a much broader pattern than he realized, one that goes far beyond oxygen specifically. Oxidation, in its full modern meaning, refers to any process where an atom loses electrons. Reduction refers to any process where an atom gains electrons. The names are historical, left over from the days when oxygen was the only known agent of this kind of change, but the concepts now extend much further. These two things always happen together, in pairs, in every single redox reaction, because an electron that leaves one atom has to arrive somewhere else. It can't simply vanish into nothing. It can't float away unattached. It must be received by another atom, matching exactly the conservation principle Lavoisier found with mass. When iron rusts, iron atoms are losing electrons to oxygen atoms from the air. Iron is being oxidized. Oxygen is being reduced. Both processes occur simultaneously, two sides of the same transaction. When your body burns sugar for energy, carbon atoms in the sugar are losing electrons to oxygen you've breathed in, releasing usable energy in the process, which your cells carefully capture and store, rather than releasing all at once as heat and flame, the way an uncontrolled fire would. This is, quietly, a slow, carefully managed, biologically controlled version of the exact same basic electron transfer that makes wood burn in a fireplace, just spread out gently across countless careful small steps inside your cells, instead of happening in one fast, uncontrolled burst. The same fundamental chemistry, oxidation and reduction, electrons moving from one atom to another, powers both a forest fire and your own quiet breathing in the dark. The difference is not in the chemistry itself, but in the speed, the control, the careful stepwise management that living systems have evolved to extract energy without destroying themselves. One more idea deserves real attention here, because it explains why some reactions that release plenty of energy and would happily proceed if given the chance, nevertheless sit around seemingly doing nothing for years, decades, or centuries. This is the idea of activation energy, the initial push of energy a reaction needs before it can get started at all, even if the overall reaction will end up releasing far more energy than that initial push required. A piece of paper sitting on your desk right now is chemically capable of burning, releasing real heat energy as its carbon bonds react with oxygen in the air. All the ingredients are present. The thermodynamics are favorable. The reaction wants to happen. But it doesn't spontaneously burst into flame while you're not looking, because the reaction needs an initial nudge of heat energy from a match or a spark to get the very first bonds breaking before the released heat from those first few reactions can sustain and spread the rest of the process on its own. There is a barrier, a hill the reaction must climb before it can roll down the other side, and until something provides the energy to climb that hill, the paper just sits there, stable, waiting. This is also where catalysts come into the picture. A catalyst is a substance that lowers the amount of activation energy a reaction needs without being consumed or permanently changed by the reaction itself. It doesn't alter the final outcome. It doesn't change the overall energy balance. It simply provides an easier, lower energy pathway for the same transformation to occur, like a guide who knows a hidden pass through the mountains, a route that avoids the highest peaks. Your body relies enormously on catalysts called enzymes, specialized molecules that speed up specific reactions inside your cells by factors of millions or even billions, allowing chemical transformations that would otherwise take years to complete safely and gently, in fractions of a second, at the mild temperature of your own living body, without needing anything like the intense heat a fire or a factory furnace requires to achieve similar transformations. Every enzyme in your body is a tiny chemical machine, precisely shaped to grab specific molecules, hold them in just the right orientation, and lower the energy barrier for their reaction, then release the products and do it again, thousands of times per second, tirelessly, quietly, all through the night. And finally, worth a gentle mention here, is the idea of polymers, extremely long molecules, built by linking together many smaller repeating units, called monomers, into extended chains, sometimes thousands or even millions of units long. This single idea, small repeating units linked into long chains, quietly explains an enormous portion of both the natural and the manufactured world around you. The proteins in your muscles are polymers, long chains of smaller units called amino acids, folded into precise three-dimensional shapes that give each protein its specific function. The starch in a slice of bread is a polymer, long chains of simple sugar units linked together, a way for plants to store energy in a compact, stable form. And the plastic in the container your leftovers are sitting in right now, in your kitchen, is also a polymer, in that case usually built from small carbon-based monomers, linked together through the same basic covalent bonding rules we walked through earlier, just repeated over and over again, thousands of times, into one enormous molecular chain. The same bonding logic that makes a water molecule, two hydrogens sharing with one oxygen, also makes the DNA in your cells, a polymer billions of units long, and the polyester in your blanket, and the cellulose in the pages of a book. Different monomers, different arrangements, same fundamental chemistry, repeated and elaborated into the vast material variety of the world. Let's step back now, out of the history and the theory, and look at where all of this is actually sitting around you tonight, quietly working, whether you're paying attention to it or not. The ideas we've walked through are not locked away in textbooks or sealed inside laboratories. They are present in your room, in your body, in the simplest objects within arm's reach. Once you start to see chemistry in the everyday, it stops being a subject you studied once and becomes something closer to a layer of reality, a quiet hum beneath everything, always there, always running. Start with the device that might have been in your hand earlier this evening, before you set it down to go to sleep. Perhaps it's on your nightstand now, dark and silent, or perhaps it's still charging, a small light glowing to show that power is flowing in. Inside that device is a small battery, and that battery is, at its heart, nothing more than a carefully controlled redox reaction. It's the same electron-losing, electron-gaining process we just talked about with rusting iron, the same fundamental transaction of electrons moving from one atom to another. The difference is that inside a battery, this process has been engineered so that instead of happening chaotically and releasing its energy as useless heat, the electrons are forced to travel through a specific external path, through the wires and circuits of your phone, doing useful electrical work along the way before they complete the reaction. The same chemistry that makes a nail crumble is harnessed to light up a screen. Inside a typical lithium battery, lithium atoms at one electrode give up electrons. They are oxidized, losing their outer electrons and becoming lithium ions. The freed electrons travel out through the circuit, powering your screen and your processor, doing the work of lighting pixels and running calculations, before returning to combine with material at the other electrode, where reduction takes place. The electrons have made a journey, a complete circuit, leaving one side and returning to the other, and along the way they have done everything you asked of your device. When you plug the battery into charge, you are, essentially, using outside electrical energy to run that whole reaction backward, forcing the electrons back to where they started, resetting the chemical system so it can release its energy again the next time you need it. Every single time you charge your phone, you are pushing a chemical reaction uphill, storing energy in chemical bonds. The same basic principle as winding a spring, just written in the language of electrons and atoms instead of mechanical tension. You are rearranging matter to hold potential, banking energy for later use, and all of it works because of the simple rules about electrons seeking stability that we walked through earlier. Now think about your own body, lying there right now. The air you just breathed in is traveling down your throat, through the branching passages of your lungs, into small sacs where the walls are thin and moist, only a single cell thick. On one side of that thin membrane is the air you just inhaled, rich with oxygen. On the other side is your blood, carrying red blood cells, each one packed with a large protein called hemoglobin. At the center of each hemoglobin molecule sits an iron atom, and it is this iron that reaches out, gently, and holds onto the oxygen. The oxygen molecules cross that thin, wet membrane and bind loosely to those iron atoms, forming a temporary partnership, a bond weak enough to break again later, but strong enough to hold for the journey through your bloodstream. This is a direct, quiet echo of the very first thing we talked about tonight. The oxygen you breathed in meeting the iron in your blood. The same meeting that has been happening since long before there were lungs to breathe it. That iron-oxygen bond is not so different, chemically, from the bond that forms when iron rusts in damp air. In both cases, iron is meeting oxygen, and electrons are shifting. But your body has found a way to make that bond loose enough, weak enough, to release the oxygen again once it reaches a cell that needs it, rather than holding on permanently the way rust does. The hemoglobin protein wraps around the iron, cradling it, controlling how tightly it grips, making sure the oxygen can let go at the right moment. It's the same chemistry as rusting, but tuned, moderated, made reversible. What would be a slow destruction of metal in the outside world becomes, inside you, a gentle, reliable delivery system. Inside nearly every one of your cells right now, that delivered oxygen is combining with sugar molecules, broken down originally from the food you ate today, in a long, carefully controlled chain of small reactions, each one managed by its own specific enzyme catalyst. The sugar is taken apart step by step, bond by bond, and at each step, a little energy is released and captured, stored in a molecule called ATP, that your cells use as a kind of energy currency. This whole process is, at the level of individual chemical bonds, remarkably similar to a fire slowly, carefully, safely burning inside every living cell of your body, all night long, keeping you warm, keeping your heart beating, keeping your thoughts moving, while you rest. The same oxidation of carbon that makes a log burn in a fireplace is happening inside you right now, just spread out across dozens of careful steps instead of one fast, uncontrolled burst, so that the energy is released in manageable packets rather than a single flare of heat. Think too about the simple act of digestion, still quietly happening somewhere in you tonight if you ate anything in the last several hours. Your stomach produces hydrochloric acid, one of the strongest common acids there is, dropping the pH inside your stomach down to somewhere around 1 or 2, acidic enough to dissolve a great deal of what you eat. This acid helps break apart the food you swallowed, unfolding the complicated folded proteins so that enzymes can reach the bonds they need to cut. It's a harsh environment, a chemical bath strong enough to damage most living tissue, and yet your stomach lining protects itself with a layer of mucus, a barrier constantly renewed, keeping the acid where it belongs. Further along in your small intestine, the environment shifts toward the basic end of the pH scale. Your body neutralizes that strong stomach acid as the food moves out of the stomach, creating the right conditions for a completely different set of enzymes to continue the job. These enzymes work best in a slightly basic environment, so the body changes the chemistry of the digestive tract as the food moves along. Acidic here, basic there, each zone tuned to the needs of the enzymes that work in it. Every bite of food you ate today has been quietly taken apart, bond by bond, by an extraordinarily precise, evolved chemical assembly line, running invisibly inside you, all without any conscious thought or effort on your part at all. You didn't have to tell your stomach to produce acid. You didn't have to instruct your pancreas to release bicarbonate to neutralize it. Your body reads the chemistry of what you ate and responds, automatically, maintaining the conditions that keep you alive. Look, too, at the room you're lying in right now, even in the dark. If there's any metal furniture or fixtures nearby, exposed to any humidity in the air, that same slow rusting reaction, iron losing electrons to oxygen, is very gradually taking place on their surfaces, over years rather than seconds. It's a slow oxidation, a quiet conversation between the metal and the moisture in the air, one atom at a time. If you washed your hands with soap before bed, you used a molecule with a fascinating dual chemical personality. One end of the soap molecule is attracted to water, hydrophilic, meaning water-loving. The other end is attracted to oil and grease, hydrophobic, meaning water-fearing but fat-loving. This split personality allows soap to surround and lift away substances that water alone could never rinse off on its own. The fat-loving ends burrow into the grease and oil, while the water-loving ends face outward, forming tiny droplets called micelles, with the grease trapped inside and the water-friendly surface facing out. These tiny droplets are small enough to be carried away in the rinse water, taking the dirt with them. It's a simple chemical trick, but it's the reason soap works at all. If you brushed your teeth before bed, the fluoride in your toothpaste is chemically strengthening the mineral structure of your tooth enamel at this very moment. Your enamel is made of a mineral called hydroxyapatite, a crystal of calcium and phosphate. Fluoride ions can swap in for some of the hydroxide ions in that crystal, forming a slightly different mineral called fluorapatite, which is more resistant to acid. The acid in your mouth comes from bacteria feeding on leftover sugar, producing acid as a waste product, and that acid slowly dissolves your enamel, which is what cavities are. Fluoride makes the enamel harder to dissolve, a small, ongoing chemical negotiation between your body, your diet, and the microorganisms that live alongside you, all happening on the surface of your teeth while you sleep. And if you look upward, out past your own room entirely, the same chemistry keeps going, all the way out to the edge of what we can see. The nitrogen and oxygen that make up nearly all of the air around you were themselves forged, originally, inside the nuclear furnaces of ancient stars, long before the Earth existed at all. Stars are chemical factories on an unimaginable scale. In their cores, lighter elements fuse into heavier ones under tremendous heat and pressure, hydrogen becoming helium, helium becoming carbon and oxygen, and on up the periodic table. When those stars eventually died, some gently shedding their outer layers, some exploding as supernovae, they scattered those newly forged elements outward across space, seeding the galaxy with the raw materials for planets and, eventually, for life. Those scattered atoms drifted for eons, gathering together with countless others to form the sun, the planets, and eventually you. The carbon in your body, the calcium in your bones, the iron in your blood, nearly every element heavier than hydrogen and helium that makes up the physical substance of you, tonight, lying in your bed, was cooked inside a star that no longer exists, billions of years before your own life began. In a genuine, literal sense, you are built from stardust, from the ashes of ancient suns. The chemistry we've spent tonight walking through, atoms combining and rearranging according to a small handful of simple, elegant rules, is the very same process that first gathered that stardust into the ordered, living, breathing shape currently listening to these words. The rules that make a grain of salt are the same rules that made you. Even the most ordinary objects around you are chemical arrangements, temporary and specific. The cotton of your sheets is mostly cellulose, a polymer of sugar units linked into long chains, each chain held to its neighbors by hydrogen bonds, the same kind of attraction that gives water its surface tension. The paint on your walls is a careful mixture of pigments, binders, and solvents, each chosen for its chemical properties, its ability to spread evenly and then harden into a stable film. The glass in your window is mostly silicon dioxide, the same chemical formula as quartz, but cooled so rapidly from its molten state that the atoms didn't have time to arrange themselves into an orderly crystal, leaving them frozen in a random, amorphous arrangement, which is why glass is transparent while sand is not. The same atoms, arranged differently, produce entirely different materials. The plastic of a water bottle, the ceramic of a coffee mug, the metal of a spoon, the wood of a bedside table. Each one is a particular arrangement of atoms, held together by the same basic bonding strategies we walked through. Ionic bonds in the ceramic, metallic bonds in the spoon, covalent bonds in the plastic and the wood, hydrogen bonds and other weaker attractions giving each material its specific texture, its specific strength, its specific way of interacting with light and heat and touch. The material world is not a random assortment. It's a library of atomic arrangements, and we can read the patterns once we know the alphabet. And then there's the air itself, the invisible ocean you're floating in right now. Roughly 78% nitrogen, 21% oxygen, with small amounts of argon, carbon dioxide, and water vapor. The nitrogen molecules, two nitrogen atoms, triple bonded together, are extraordinarily stable, almost inert, which is why they make up most of the air without reacting with much of anything. They are the background, the buffer, the quiet majority. The oxygen molecules are the active ingredient, ready to combine, ready to receive electrons, the breath that fuels your cells. The carbon dioxide is there in trace amounts, exhaled by you and by every other breathing creature, absorbed by plants and turned back into oxygen through photosynthesis, a slow global cycle of gas exchange that links your breath to every leaf on every tree. You breathe out what the plants breathe in, they breathe out what you breathe in. It's a chemical partnership spanning the whole planet, and it's happening right now, in the dark, while you rest. There are still real, open questions sitting underneath everything we've talked about tonight. Places where even the most careful chemists and physicists working today do not have complete, settled answers. And it's worth spending a little time with these, gently, because there's something calming about knowing that even a science as mature and successful as chemistry still has genuine mystery left inside it. The unknown is not a failure. It's not a sign that the whole enterprise is shaky. It's simply the edge of the map, the place where the questions get deeper and the answers get harder. And that's been true at every stage of this long story. Every generation of chemists pushed the boundary a little further, and every generation left new questions for the ones who came after. One of the strangest and deepest questions concerns why chemical bonding works the way it does at all, once you look closely enough. The picture we walked through tonight, electrons occupying shells, atoms giving, taking, or sharing electrons to reach a stable full shell, is a wonderfully useful simplification. It explains an enormous amount of real chemistry correctly. It tells you why salt forms, why water is H2O and not something else, why the noble gases sit aloof and undisturbed, while sodium and chlorine rush toward each other. For most everyday purposes, this picture is enough. It works. It makes accurate predictions. But if you look closer, using the tools of quantum mechanics, the picture gets stranger. Electrons don't actually orbit the nucleus the way tiny planets orbit a sun, occupying clean, simple shells like layers of an onion. They exist instead as probability clouds, strange three-dimensional regions of space, describing where an electron is more or less likely to be found at any given moment, without ever having one single definite location, the way a marble does. You can't point to a spot and say, the electron is there. You can only say, the electron is more likely to be in this region than that one, and here is the shape of that likelihood. An electron, in this deeper picture, is not really a tiny ball circling the nucleus, but something closer to a fuzzy, shifting cloud of possibility. A smear of potential locations, and the neat shells we described earlier are really a simplified stand-in for the shapes these probability clouds naturally take. The shells are not actual orbits. They are more like energy levels, regions where electrons with a certain amount of energy are most likely to be found. And the way electrons fill these regions, the way they pair up and spread out, determines everything about how atoms bond. The simple rules we learned, 2 electrons in the first shell, 8 in the next, are themselves simplifications of deeper mathematical patterns, patterns that emerge from the quantum mechanical behavior of electrons. Chemists and physicists can calculate these strange probability clouds with remarkable precision for simple atoms. For hydrogen, with its single electron, the mathematics is solvable exactly, and the predictions match experimental measurements to an extraordinary degree. But for anything more complicated than a handful of atoms bonded together, the mathematics becomes so demanding that even the most powerful supercomputers in the world today can only approximate the true, complete answer, rather than calculate it exactly. There is something genuinely strange sitting at the very foundation of the ordinary table salt in your kitchen, a layer of reality where the tidy, comfortable rules we use every day give way to something far more probabilistic and uncertain, something that still, even after a century of quantum mechanics, resists easy human intuition. We can use the rules, we can apply them with great success, but the underlying reality they describe is not something the human mind can easily picture, and that's a humbling thing to sit with. There's also the ongoing challenge of understanding exactly how life first emerged from simple, lifeless chemistry, a question that sits right at the border between chemistry and biology and remains genuinely unresolved. We understand, in reasonably good detail, an enormous number of individual chemical reactions that occur inside living cells today. We know how enzymes work, how DNA copies itself, how proteins fold into their specific shapes, how energy is captured and stored and released. The chemistry of life as it exists now is mapped out in extraordinary detail, a vast atlas of interconnected reactions, each one understood at the molecular level. But the deeper question of precisely how, billions of years ago on a young and lifeless Earth, ordinary chemical reactions among simple molecules gradually organize themselves into the first entity capable of copying itself, of maintaining its own boundaries, of responding to its environment, the first true spark of what we'd call life, remains an active area of real scientific research, with several competing ideas and no single, complete, agreed-upon answer yet. It's not that we have no ideas. We have many ideas, each with some evidence behind it, each with its own strengths and gaps. Perhaps life began near deep-sea hydrothermal vents, where warm, mineral-rich water met colder ocean water, creating chemical gradients that could drive the formation of complex molecules. Perhaps it began in shallow tidal pools, where the cycling of wet and dry conditions concentrated organic molecules and encouraged them to link together. Perhaps it began elsewhere entirely and arrived on Earth carried by meteorites or comets, though that only pushes the question back to another location. Researchers have successfully created some of the necessary building blocks, amino acids and simple sugars, under laboratory conditions meant to mimic the early Earth. In the 1950s, Stanley Miller and Harold Urey ran a now famous experiment in which they sealed water, methane, ammonia, and hydrogen in a glass apparatus and passed electric sparks through the mixture to simulate lightning. Within days, the water had turned brown and was found to contain several amino acids, the building blocks of proteins. The experiment showed that under conditions thought to resemble the early Earth, simple molecules could spontaneously form more complex ones, no life required. More recent work has shown that the building blocks of RNA, a molecule related to DNA and capable of both storing information and catalyzing reactions, can also form under prebiotic conditions. And remarkable work continues on understanding how simple molecular chains might have first learned to copy themselves, how a collection of molecules might have crossed the threshold from a set of chemical reactions to something that could be called a living system. But the full, complete chemical pathway, from a lifeless mixture of simple molecules to the first genuinely living, self-sustaining, self-replicating chemical system, remains one of the most significant open questions in all of science, quietly waiting, somewhere in humanity's future, for a more complete answer. There is also a beautiful and strange puzzle involving the handedness of certain molecules, something chemists call chirality. The word comes from the Greek for hand, and the image is exactly right. Many organic molecules, including nearly all the amino acids that build the proteins inside your body right now, can exist in two versions that are mirror images of one another, exactly the way your left hand and your right hand are mirror images. They have the same atoms, the same bonds, the same overall structure, but they are not identical. One is the mirror reflection of the other, and no matter how you rotate them, you cannot superimpose one onto the other, just as you cannot put a left-handed glove onto a right hand. These two versions, called enantiomers, are identical in almost every measurable way. They have the same melting point, the same boiling point, the same solubility, the same density. They behave the same in most chemical environments. But in a biological context, that handedness matters enormously. Enzymes, the protein catalysts in your body, are themselves chiral, built from chiral amino acids and folded into chiral shapes. An enzyme that fits one enantiomer perfectly, like a lock accepting the right key, will often fail entirely to interact with its mirror image. It would be like trying to shake hands with someone's reflection. The shape is wrong, the fit is wrong. And yet, life on Earth, for reasons that remain only partially understood, overwhelmingly uses only one of these two mirror image versions. The amino acids in your proteins are almost exclusively left-handed. The sugars in your DNA are right-handed. Across essentially every living thing that has ever been studied, from bacteria to blue whales, this preference holds. Why life settled so completely on one-handedness rather than the other, and whether that choice was some early accident locked in and inherited by everything that came after, or whether it reflects some deeper, still undetected chemical or physical reason, remains a genuinely open and actively studied question. It could be that the first self-replicating system happened to use left-handed amino acids by pure chance, and everything since has inherited that arbitrary choice. It could be that there is some subtle physical reason, perhaps involving the weak nuclear force, that slightly favors one-handedness over the other. The question is still open, still being investigated, a small mystery with large implications. And finally, there's a much larger and stranger mystery, one that reaches beyond chemistry into cosmology itself, but that chemistry has quietly bumped up against in an important way. When physicists study the very early universe, they find that the fundamental laws of physics appear to predict that matter and something called antimatter, a kind of mirror image counterpart to ordinary matter where every particle's electric charge is flipped, should have been created in almost exactly equal amounts during the earliest moments after the beginning of the universe. For every particle of matter, a corresponding particle of antimatter, identical in mass but opposite in charge. And when matter and antimatter meet, they annihilate each other completely, converting entirely into pure energy, a burst of light, leaving nothing of either behind. If the early universe had truly produced perfectly equal amounts of both, virtually all of it should have annihilated together almost immediately. The matter and antimatter would have found each other in those first dense moments, and the result would have been a universe filled only with light and energy, and essentially no matter at all. No stars, no planets, no atoms, no chemistry, no you. And yet, here we are, made of ordinary matter, in a universe still full of galaxies and stars and planets, and, apparently, very little detectable antimatter anywhere at all. We don't see regions of space made of antimatter. We don't see the characteristic radiation that would come from boundaries where matter and antimatter regions meet. As far as we can tell, the observable universe is made almost entirely of ordinary matter. Something, in those first fleeting moments after the beginning, tipped the balance ever so slightly in favor of ordinary matter over antimatter. The margin must have been tiny. For every billion particles of antimatter, perhaps there were 1,000,001 particles of matter, 1,000,000,000 annihilated with 1,000,000,000, leaving just that one leftover particle of matter, and it is from those leftover particles, those tiny survivors of the great annihilation, that everything we see is built. The imbalance was small enough that it took billions of years to fully play out, yet decisive enough to leave us with an entire universe worth of atoms, rather than an empty, dark expanse of pure light. Precisely what caused that tiny imbalance, what process in those earliest moments favored matter over antimatter by that minuscule but crucial margin, remains one of the true unanswered questions sitting underneath all of physics and all of chemistry alike. It is, in a sense, the very first mystery, the one that had to resolve itself before there could be any atoms at all, for a person named Democritus to guess about, thousands of years later, on a warm afternoon in ancient Greece. Before there could be a periodic table, before there could be a Lavoisier weighing his sealed jars, before there could be stars to forge the elements that would eventually become you, there had to be matter rather than nothing, and we still don't fully know why that is. These open questions are not flaws in the edifice of chemistry. They are the frontier. They are the places where the map still reads, "Here be dragons," and they remind us that the story we've been tracing tonight is not finished. It is still being written, by researchers in laboratories and observatories and supercomputer centers around the world. The broad outlines are clear and well tested. The periodic table is not going anywhere. The conservation of mass is not going anywhere. But the details, the deep reasons, the connections to other fields and other mysteries, those are still being worked out, and they will keep being worked out long after tonight is over. And there's something restful in that, something reassuring. The world is not fully explained. There is still room for wonder, still room for new questions, still room for someone to notice something that nobody has noticed before, the way a person on a riverbank once noticed that a green rock changed in the fire, and everything followed from there. By now you may have drifted in and out a few times. That's exactly right. There's nothing to catch up on. Everything has been settling quietly, whether you were following closely or not. The way sound settles into a room, the way warmth settles into a blanket. You don't have to reach for any of it. It's already here, waiting, the same way it was waiting before you started listening, the same way it will be waiting tomorrow night if you decide to come back. There is no urgency in any of this, no deadline, no test, just the ideas, resting quietly, available whenever you want them. If you were to hold all of tonight in one single image, a picture you could return to when you want to remember what chemistry actually is, beneath all the names and dates and technical language, it would be this. Picture a vast, quiet darkness, and scattered through it, an almost unimaginable number of tiny points of matter. Each one is built from a nucleus so small and dense it would be invisible even under a strong microscope, surrounded by a soft, uncertain cloud of electrons, more like a hum of possibility than a solid thing. These tiny points are not crowded together. There is enormous space between them, even in what we call solid objects. Each one is mostly emptiness, with that tiny dense heart at the center and that diffuse cloud of probability around it, like a minute solar system where the planets are not objects but suggestions, likelihoods, regions where something might be found. Most of these tiny points are simply drifting, alone, through that empty space. They are complete in themselves, their outer electron shells full, their charges balanced, their energy settled into the lowest comfortable state they can find. They don't need anything. They don't seek anything. They just exist, quiet and self-contained, like the noble gases we talked about earlier, drifting undisturbed through the world. But every so often, two of these points meet in just the right way, with just the right leftover space in their outer clouds. And when they meet like that, something happens between them. An offering, an electron given away entirely, like sodium handing its lone outer electron to chlorine. Or a taking, one atom receiving what another is ready to release. Or a quiet, mutual sharing, two atoms holding a pair of electrons between them, the way two people might hold a single umbrella in the rain, both benefiting, neither one fully possessing it alone. And where there were two separate small points, there is now one slightly larger, slightly more complete arrangement, more stable than either point was on its own, a new substance, a new set of properties, something that did not exist before and now does. That is chemistry. That meeting, that exchange, that sharing, that is the entire story. Everything else we talked about tonight, the ancient philosophers guessing at fire and water and earth and air, the alchemists distilling and heating and hoping for gold, Lavoisier weighing his sealed jars with such obsessive care, Dalton staring at his fixed ratios of hydrogen and oxygen and realizing they were counting something real, Mendeleev laying his cards out on a table and trusting the gaps he found, Thomson and Rutherford peering inside the atom itself and finding it was mostly empty space with a tiny dense heart. Every single bit of that long, slow human story was really just people, one careful observation at a time, uncovering the true shape of that single image. Tiny points of matter, seeking stability, occasionally finding each other, occasionally letting go, occasionally holding on so tightly that something new comes into being. A grain of salt, a particular arrangement of sodium and chlorine ions, held together by nothing more than the attraction of opposite charges. A drop of water, two hydrogens sharing electrons with one oxygen. a simple partnership repeated countless times in every ocean, every cloud, every cell in your body. A single sugar molecule, a ring of carbon atoms with oxygen and hydrogen attached, waiting to be taken apart by enzymes to release the energy stored in its bonds. A strand of the very DNA curled up inside every one of your billions of cells right now. A polymer billions of units long, encoding the instructions for building and maintaining the particular temporary arrangement of matter that is you. And here is the part worth sitting with, quietly, as you drift the rest of the way toward sleep tonight. You are not separate from any of this. You are not a person who occasionally interacts with chemistry when you cook dinner, or take a medication, or watch a battery charge. You are not an observer standing outside the system, looking in. You are the system. You are chemistry, organized into an extraordinarily elaborate, temporary, self-sustaining pattern, built from the very same handful of simple rules we walk through tonight. Carbon chaining to carbon, forming the backbone of your proteins and your DNA, and the fat that insulates your nerves. Hydrogen sharing with oxygen, forming the water that makes up more than half of your body's weight. The solvent, in which all your other chemistry takes place. Iron holding gently onto oxygen inside your blood, and releasing it again exactly when and where it's needed. A controlled, reversible version of the same reaction that turns a nail to rust. Every element in your body is older than your own birth, older than the earth itself, gathered originally from stars that lived and died long before the earth ever formed. Every bond inside you follows the same quiet logic that governs a grain of table salt or a bubble of gas rising through a glass of water. Giving, taking, sharing, always moving gently toward whatever arrangement is most stable, most settled, most at rest. This is not a metaphor. It is not a poetic way of speaking. It is literally, physically true. The atoms in your body right now were forged in the cores of stars that no longer exist. The hydrogen in your water is older still, dating back to the first few minutes after the universe began, when the first protons and electrons cooled enough to bind together into the simplest element. The carbon that forms the backbone of every organic molecule in you was made by the fusion of 3 helium nuclei inside a star, a process called the triple alpha process, one of the key reactions that turns the primordial hydrogen and helium of the early universe into the heavier elements that make planets and life possible. The iron in your blood was forged in the final stages of a massive star's life, the last element that can be produced by fusion, before the star runs out of energy and collapses. Every breath you take brings in oxygen that was released by the explosion of a dying star, scattered across space, gathered into a cloud that eventually collapsed to form our solar system. You are, in the most direct and literal sense, a piece of the universe that has become temporarily aware of itself, a configuration of stardust that can look back at the stars and understand, at least in part, where it came from. So as you lie there now, in the dark, in your own room, let yourself feel, just for a moment, the enormous quiet machinery that is still running inside you, without any effort from you at all. You don't have to manage it, you don't have to supervise it, you don't even have to be awake for it. The oxygen is still crossing into your blood, moving from the air in your lungs across that thin, wet membrane, finding the iron atoms waiting in your hemoglobin, binding loosely, gently, ready to let go again when the time comes. The iron is still holding it, carrying it through your arteries, releasing it into your tissues where it's needed. The sugar from today's meals is still being gently, carefully taken apart, bond by bond, in a long cascade of enzyme-controlled reactions, each step releasing a small amount of energy, each step managed by a specific protein catalyst that lowers the activation energy and makes the reaction possible at body temperature. The carbon dioxide you've produced is being carried back to your lungs, diffusing back across that same thin membrane, waiting to be exhaled with your next breath. Your enzymes are still working, millions of them in every cell, each one a tiny machine, precisely shaped to grab specific molecules, hold them in just the right orientation, and speed up the reaction that needs to happen. Then release the products and do it again, thousands of times per second, all through the night. None of this needs you to be awake. None of this needs you to understand it, or remember it, or think about it at all. It was happening in you before you ever learned the word chemistry. It was happening in you before you were born, when you were still a tiny cluster of cells, each one dividing and differentiating according to chemical signals, each one reading the same DNA but expressing different genes, becoming muscle or nerve or bone or blood. It will keep happening in you tonight, steadily, quietly, while you rest, and it will keep happening tomorrow and the day after that, for as long as you live. You are not running this machinery. You are this machinery, this temporary, beautiful, self-maintaining pattern of atoms, held together by the same bonds we've been talking about all evening. Somewhere above you, if you could see through the ceiling and the sky, the same nitrogen and oxygen atoms that first came together inside a dying star are still drifting through the air of your room. Some of them are the very same atoms that have passed through countless other sleeping bodies before yours, breathed in and breathed out, over and over, for as long as there has been breath to breathe. The atoms that make up the air you're breathing right now have been circulating through the atmosphere for billions of years. Some of them were once in the lungs of dinosaurs. Some of them were dissolved in ancient oceans. Some of them were locked inside rocks for millions of years before being released by volcanic eruptions. They cycle through the world endlessly, borrowed for a moment, then returned, passed along to the next living thing that needs them. You are not an isolated system. You are an open system, constantly exchanging matter with the world around you, breathing in and breathing out, taking in and releasing, part of a cycle that has been running since the first living cells appeared on Earth. You are, tonight, one small, brief, particular arrangement of very old material, held together for a while by nothing more than a handful of simple, elegant rules about giving, taking, and sharing. The rules are not complicated. An atom with an incomplete outer shell seeks stability. It gives, takes, or shares electrons. Those simple actions, repeated in different combinations and different sequences, produce the entire variety of the material world, from the salt on your table to the neurons firing in your brain. And right now, as you lie here in the dark, that arrangement is resting, settling gently into stillness, the way all of that ancient material eventually seems to want to rest. Your breathing is slowing, your muscles are relaxing, the chemistry inside you is shifting from the active, alert mode of daytime to the quieter, restorative mode of sleep. Hormones are being released, memories are being consolidated, cells are being repaired, all of it chemistry, all of it following the same rules, all of it happening without your conscious direction. So let it happen. Let the machinery run. Let the atoms do what they know how to do, what they have been doing since long before there was anyone to watch them. There is nothing you need to hold on to, nothing you need to figure out, nothing you need to solve before you can rest. The chemistry will keep going, whether you're following along or not, whether you remember a word of this or not. You are part of it, made of it, sustained by it, and in a little while, when you fall fully asleep, you will still be part of it, breathing in, breathing out, exchanging atoms with the universe, a brief and lovely pattern of stardust, settling quietly into the dark. So here you are, still drifting, still resting, the weight of your body settling deeper into the mattress, the pillow, the quiet dark around you. And if some part of you is still listening, still awake enough to catch these words, let's take one more gentle walk through a few ideas that deserve a little more time, a little more space to unfold. These are not new topics so much as deeper layers beneath the ones we've already touched, the kind of understanding that comes not from learning something different, but from looking more closely at what you already know. Let's return to water, because water is the quiet hero of everything we've been talking about, and it deserves its own moment of attention. Water is such a familiar substance that it's easy to overlook how peculiar it actually is, how many of its properties are genuinely unusual when compared to other liquids, and how much of life depends on those unusual properties. The simple water molecule, two hydrogens sharing electrons with one oxygen, bent at an angle of about 104 degrees, not straight but kinked, like a shallow V, turns out to be shaped in a way that makes almost everything else possible. Because oxygen pulls on shared electrons more strongly than hydrogen does, the oxygen end of a water molecule carries a slight negative charge, and the hydrogen ends carry a slight positive charge. The molecule is polar, meaning it has a positive side and a negative side, like a tiny magnet. This polarity means that water molecules are drawn to one another, the positive hydrogen of one molecule attracted to the negative oxygen of its neighbor. These attractions are called hydrogen bonds, and they are weaker than the covalent bonds that hold the atoms together inside a single molecule, but they are strong enough, collectively, to give water a whole set of behaviors that nothing else quite matches. Because of hydrogen bonding, water can absorb a large amount of heat without its temperature rising very much. You can add energy to water, and instead of getting dramatically hotter, much of that energy goes into breaking the hydrogen bonds between molecules, loosening the structure without raising the temperature. This is why the ocean stays relatively cool even under a blazing sun, and why your body can regulate its temperature so effectively. You are mostly water, and that water acts as a thermal buffer, absorbing the heat your cells generate and releasing it slowly, keeping you within the narrow temperature range that your enzymes need to function. Because of hydrogen bonding, water also expands when it freezes. This is genuinely odd. Most substances contract as they cool and become denser in their solid form than in their liquid form. But water, as it freezes, arranges itself into a crystal lattice held open by hydrogen bonds, and the solid form, ice, is less dense than the liquid. Ice floats. If ice sank, if frozen water were denser than liquid water, lakes and oceans would freeze from the bottom up, and life as we know it might never have gained a foothold. The floating ice insulates the water beneath, allowing life to survive through winters, allowing the chemistry of living things to continue in the cold dark under a frozen surface. Because water is polar, it is also an extraordinary solvent, capable of dissolving a wider range of substances than almost any other liquid. When you stir salt into water, the positive ends of the water molecules cluster around the negative chloride ions, and the negative ends cluster around the positive sodium ions, pulling the crystal lattice apart, surrounding each ion in a shell of water molecules, carrying it away into solution. This is why your blood can carry dissolved nutrients, why your cells can receive the molecules they need, why chemical reactions can happen in the liquid environment inside you, rather than requiring the harsh conditions of a furnace or a laboratory. Water is the medium in which almost all of your chemistry takes place. It is not just a background, it is an active participant, shaping the way molecules interact, bringing them together, holding them apart, providing the stage on which the entire drama of your metabolism unfolds. And speaking of stages, let's turn now to the quiet, patient work of enzymes, because we touched on them earlier, but they deserve a closer look. An enzyme is a protein, a long chain of amino acids folded into a precise three-dimensional shape, and that shape is everything. The folding is not random. It is determined by the sequence of amino acids, which is determined by the sequence of bases in your DNA, which was inherited from your parents and shaped by billions of years of evolution. Each enzyme has a specific shape, with a specific pocket or groove called the active site, and this active site is shaped to fit a specific molecule, or a small set of related molecules, the way a key fits a lock. When the right molecule drifts into the active site, it binds there, held by the same kinds of attractions we've been talking about all night: hydrogen bonds, ionic attractions, brief temporary sharing of electrons. And once the molecule is held in place, the enzyme does something subtle but powerful. It stresses the bonds of the molecule. It bends it slightly, twists it, holds it in a position that makes a particular reaction easier. The activation energy, that initial hill the reaction needs to climb, is lowered. The reaction proceeds, sometimes millions of times faster than it would without the enzyme, and when it's done, the products are released, and the enzyme returns to its original shape, ready to do it all again. What makes this even more elegant is that enzymes can be regulated. Your cells can turn enzymes on and off, speed them up and slow them down, in response to signals from elsewhere in the body. A molecule that is not the enzyme's usual target can bind to a different site on the enzyme, changing its shape slightly, making the active site more or less receptive. This is how hormones work. This is how your body coordinates the chemistry happening in billions of cells at once. Insulin, for example, binds to receptors on the surface of your cells and triggers a cascade of signals that ultimately activate enzymes involved in taking up sugar from your blood. It's chemistry, but it's chemistry with feedback loops, with sensors and switches, with the ability to respond to changing conditions. It's not just a set of reactions, it's a system, a network, a web of interconnected chemical pathways that regulate themselves. Another idea that rewards a closer look is the nature of carbon, which we mentioned as the backbone of organic chemistry, but whose full significance is worth sitting with. Carbon's ability to form 4 bonds, and to bond with other carbon atoms in long chains, is what makes the complexity of life possible. But there's more to it than that. Carbon can form single bonds, which are flexible and allow rotation, or double bonds, which are rigid and lock atoms into a fixed plane. This combination of flexible and rigid bonds allows carbon-based molecules to fold into precise shapes that are essential for the function of proteins and DNA and every other biomolecule. Carbon can also bond to a wide variety of other elements: hydrogen, oxygen, nitrogen, sulfur, phosphorus, and more, creating an enormous range of possible structures, each with its own chemical personality. A carbon chain decorated with oxygen atoms will be hydrophilic, attracted to water. A carbon chain covered mostly in hydrogen will be hydrophobic, repelled by water, which is how cell membranes form. The membrane that surrounds each of your cells is made of phospholipids, molecules with a hydrophilic head and 2 hydrophobic tails, which naturally arrange themselves into a double layer, heads facing outward toward the water on both sides, tails tucked away inside. This spontaneous self-assembly, driven by nothing more than the tendency of hydrophobic molecules to avoid water, is what creates the boundary between your cells and their environment, the barrier that keeps your chemistry organized and contained. Let's also spend a moment with the idea of energy flow, because it runs through everything we've discussed but hasn't been named directly. Every chemical reaction involves energy. Some release energy, like burning wood or the slow oxidation of sugar in your cells. These are called exothermic reactions, energy flowing outward. Others absorb energy, like the splitting of water into hydrogen and oxygen, which requires an input of electrical energy to proceed. These are called endothermic reactions, energy flowing inward. But the deeper point is that energy and chemistry are inseparable. The same electrons that shift when bonds break and form are also carriers of energy. A bond represents a certain amount of stored energy, and when that bond breaks and new bonds form, the difference in energy between the old arrangement and the new one is either released or absorbed. Your body is, among other things, an energy management system. The food you eat contains molecules with energy stored in their bonds, mostly in the form of carbohydrates and fats. Your digestive system breaks these down into simpler molecules, which are absorbed into your bloodstream and delivered to your cells. Inside your cells, these molecules enter the slow, stepwise oxidation pathways we mentioned earlier, and the energy released at each step is captured in the form of ATP, a molecule that acts as a kind of energy currency. When a cell needs energy to do something, to contract a muscle fiber, to pump ions across a membrane, to build a new protein, it spends ATP, breaking one of its high-energy bonds and using the released energy to drive the needed reaction. The ATP is then regenerated, recharged by the energy from food, and the cycle continues, billions of times per second, across all the cells of your body, right now, as you rest. This brings us back, as so many things do, to oxygen. The reason oxygen is so central to your energy metabolism is that it is exceptionally good at accepting electrons. It is, in the language of chemistry, a powerful oxidizing agent. When electrons flow from the carbon atoms in your food to the oxygen atoms you breathe in, they move from a higher energy state to a lower energy state, and that drop in energy is what your cells capture and use. Oxygen is the final electron acceptor in the long chain of reactions that extracts energy from your food. Without it, the chain backs up. The flow of electrons stops and the energy capture ceases. This is why you breathe. This is why your blood carries oxygen to every cell. This is why the meeting of oxygen and iron in your lungs is the quiet, essential event we began with, the moment that keeps all the rest of it going. And if we pull back even further, the ultimate source of all this energy is the sun. Plants capture sunlight and use its energy to split water and combine carbon dioxide into sugars, storing the sun's energy in chemical bonds. Animals eat plants or eat other animals that ate plants and release that stored energy through the slow oxidation we call metabolism. The fire that burns in a fireplace and the fire that burns gently in your cells are both powered by sunlight, captured and stored and released across different timescales. The oxygen you breathe is a byproduct of photosynthesis, released by plants and cyanobacteria over billions of years, gradually transforming the Earth's atmosphere from a mixture devoid of oxygen to one that is 21% oxygen, the breathable air that makes your kind of life possible. You are, in a direct chemical sense, running on sunlight, processed through the green machinery of leaves and the quiet labor of your own cells. So as you lie here, drifting further now, perhaps barely holding on to these words, let these ideas settle into the background like a low, steady hum. Water with its bent shape and its hydrogen bonds, making everything dissolve and flow and float. Enzymes with their precise folded shapes, quietly lowering the hills that reactions need to climb. Carbon, with its 4 bonds building the long, flexible chains that twist and fold into the machinery of life. Energy, flowing from sun to plant to animal to cell, carried by electrons shifting from one atom to another, all of it connected, all of it following the same simple rules, all of it happening inside you, around you, through you, while you rest. There is no hurry, there is nothing to memorize. The ideas will wait. The chemistry will keep going. Just let yourself sink a little deeper and know that everything is running exactly as it should. Let's return now to something we passed by earlier, something that deserves more than a passing mention, because it sits at the heart of what makes life possible in a chemical sense. This is the quiet, constant work of maintaining balance. Your body, right now as you lie there, is performing an almost uncountable number of small adjustments every second, keeping your internal chemistry within the narrow ranges that your cells can tolerate. This process has a name, homeostasis, but the name matters less than the idea. The idea is that living systems are not passive. They are not simply drifting with whatever chemical changes happen around them. They are actively, constantly pushing back, adjusting, compensating, keeping things steady. Think about temperature. Your body needs to stay within a few degrees of 37 Celsius, and it works to maintain that temperature whether you're in a cold room or a warm one. If you get too warm, blood vessels near your skin widen, letting more heat escape. If you get too cold, they narrow, conserving heat. You might shiver, generating warmth through rapid muscle contractions. All of this is chemistry in motion, signals sent through your nervous system, hormones released into your bloodstream, enzymes speeding up or slowing down their reactions in response to changing conditions. The set point, the target temperature, is maintained by a network of chemical feedback loops that monitor, compare, and adjust. Think about blood sugar. After you eat, the level of glucose in your blood rises. Your pancreas senses this and releases insulin, a protein hormone that signals your cells to take up glucose, to use it for energy or store it for later. If your blood sugar drops too low, your pancreas releases a different hormone, glucagon, which signals your liver to release stored glucose back into the blood. These two hormones, insulin and glucagon, are chemical opposites, working against each other to keep your blood sugar in a safe middle range. Too high for too long damages tissues. Too low starves your brain of fuel. The balance must be maintained, and it is, through chemistry, through the shaped fit of hormones into receptors, through the cascades of enzymes they activate, through the careful regulation of every step in the pathway. Think about pH. We touched on this earlier, but it's worth returning to. Your blood pH is kept between 7.35 and 7.45, just slightly basic. If it drops below 7, you enter a state called acidosis. If it rises above 7.8, alkalosis. Both are dangerous. Both can be fatal if not corrected. So your body maintains a buffer system, a mixture of carbonic acid and bicarbonate ions that can absorb excess hydrogen ions when the blood gets too acidic, or release hydrogen ions when it gets too basic. This buffer system works in tandem with your lungs, which can speed up or slow down your breathing to adjust the level of carbon dioxide in your blood, since carbon dioxide dissolves in water to form carbonic acid. If your blood becomes too acidic, you breathe faster, blowing off carbon dioxide, shifting the chemical equilibrium toward less acid. If your blood becomes too basic, you breathe slower, retaining carbon dioxide, shifting the equilibrium the other way. Your kidneys also play a role, excreting or retaining hydrogen ions and bicarbonate as needed, a slower but more powerful adjustment that works over hours and days. All of this is chemistry. It's the same acid-base chemistry we talked about with lemons and baking soda and the pH scale, but it's happening inside you, right now, in a carefully orchestrated dance of molecules, each one responding to the presence of others, each one part of a system that maintains the conditions necessary for your continued existence. You don't have to think about it, you don't have to manage it. The chemistry manages itself, through feedback loops that evolved over billions of years, loops that are written into the structure of your proteins and the behavior of your cells. Let's also spend a moment with the chemistry of your nervous system, because it's happening right now, even as you drift towards sleep, and it's one of the more elegant examples of chemistry in action. Your nerve cells, your neurons, communicate with each other using a combination of electrical and chemical signals. A neuron at rest maintains a difference in electrical charge across its membrane, negative inside, positive outside, by pumping ions, sodium, potassium, chloride, calcium, in and out through specialized protein channels. This ion pumping is active, energy-consuming work, and it's what keeps your neurons ready to fire. When a signal arrives, ion channels open, sodium rushes in, and the electrical charge flips briefly, creating a spike of positive charge that travels down the length of the neuron like a wave. When this electrical wave reaches the end of the neuron, at a junction called a synapse, it triggers the release of chemical messengers, neurotransmitters, small molecules that cross the tiny gap to the next neuron and bind to receptors there, starting the electrical signal all over again in the next cell. Serotonin, dopamine, acetylcholine, GABA, glutamate, each one has its own shape, its own receptors, its own effects. Some excite the next neuron, making it more likely to fire. Others inhibit it, making it less likely. The balance of excitation and inhibition across billions of neurons and trillions of synapses is what makes your brain work. It's chemistry, signaling chemistry, controlled by chemistry, interpreted by chemistry. Right now, as you lie in the dark, the chemistry of your brain is shifting. Your levels of serotonin and norepinephrine, neurotransmitters associated with wakefulness and alertness, are decreasing. Your levels of GABA, an inhibitory neurotransmitter that quiets neural activity, are increasing. Your pineal gland is releasing melatonin, a hormone derived from serotonin, which signals to your body that it's time to rest. Adenosine, a byproduct of energy metabolism that builds up in your brain throughout the day, is binding to its receptors, creating the sensation of sleep pressure, the feeling of drowsiness that makes your eyelids heavy. If you've ever had caffeine, you've experienced the chemistry of adenosine firsthand. Caffeine works by blocking adenosine receptors, preventing adenosine from binding and thus temporarily preventing you from feeling tired. It's a chemical competition, a molecular shape fitting into a receptor and blocking the natural signal, a small pharmacological trick that works because of the same lock-and-key principle that governs all of biochemistry. Even the process of falling asleep involves chemistry. As you drift deeper, your brain cycles through different stages, each characterized by different patterns of neurotransmitter release and different patterns of electrical activity. During deep, slow-wave sleep, your brain releases growth hormone, which stimulates tissue repair and growth. During REM sleep, when dreams are most vivid, your brain's chemistry shifts again, with acetylcholine levels rising and other neurotransmitters falling silent, a chemical state quite different from either waking or deep sleep. All of this happens without your direction. All of this happens whether you understand it or not. The chemistry of sleep is running its course, carrying you gently from one stage to the next, restoring and repairing and consolidating while you rest. And since we're speaking of the brain, let's touch on something that sits at the very boundary of what we understand, the relationship between chemistry and thought itself. Your thoughts, your memories, your sense of who you are all, at one level, chemical phenomena. A memory is not a single molecule, but it depends on molecules. When you learn something new, when you form a memory, the connections between certain neurons strengthen, a process called long-term potentiation. This strengthening involves chemical changes, the insertion of new receptor proteins into the synapse, the growth of new synaptic connections, the activation of genes that produce the proteins needed to reinforce the active pathway. The memory is stored in the pattern of strengthened connections, but the pattern itself is built and maintained by chemistry. Your sense of self, your personality, your moods, all of these are, at their physical foundation, patterns of chemical activity in a network of billions of neurons. Change the chemistry with a medication or a hormone or a drug, and you change the experience. This is not reductionist in any cold or dismissive sense. It's simply to say that chemistry is the language in which the brain writes its story, and the story is no less meaningful for being written in molecules. There's one more chemical cycle worth mentioning, one that connects your body to the larger rhythms of the planet. This is the circadian rhythm, your internal clock, which keeps your body synchronized with the cycle of day and night. At its core, the circadian clock is a chemical oscillator, a feedback loop of proteins that build up and break down in a roughly 24-hour cycle. The genes that produce these clock proteins are activated, the proteins are made, they accumulate, and when they reach a certain level, they turn off the genes that produce them. Then the proteins degrade, their levels fall, and the genes turn back on. This cycle takes about a day, and it runs in nearly every cell of your body, not just in your brain. Your liver has a clock, your muscles have a clock, your fat cells have a clock. All of them are synchronized by a master clock in your brain, a small region called the suprachiasmatic nucleus, which receives input from your eyes about the presence or absence of light. Light hits your retina, a signal travels to the master clock, and the clock adjusts, resetting itself each day to stay aligned with the sun. This is why jet lag feels the way it does. Your internal clocks have become desynchronized from the external day, and it takes time for the chemical oscillators in all your different tissues to realign. So as you lie here in the dark, your circadian clock is doing what it does every night. It's signaling the release of melatonin. It's lowering your body temperature slightly, because a small drop in core temperature helps facilitate sleep. It's adjusting the sensitivity of your insulin receptors, because your body processes sugar differently at night than during the day. All of these adjustments are chemical, and all of them are timed, orchestrated by the slow oscillation of proteins being made and degraded, rising and falling, like a chemical tide inside every cell. And if we pull back even further, beyond your own body, beyond your own room, the same principles of chemical regulation and balance operate at the scale of the entire planet. The carbon cycle, the nitrogen cycle, the oxygen cycle, These are global chemical systems with feedback loops and buffers and equilibria, just like the ones inside your body, only larger and slower. Plants take carbon dioxide from the air and turn it into organic matter. Animals and fungi and bacteria break that organic matter back down and return carbon dioxide to the air. The ocean absorbs carbon dioxide and releases it, acting as a vast chemical buffer for the atmosphere. The nitrogen in the air is fixed by bacteria into forms that plants can use, then passed up the food chain, then returned to the air by other bacteria. The oxygen you breathe is replenished by photosynthesis and consumed by respiration and combustion in a global balance that has been maintained, with some variation, for hundreds of millions of years. These global cycles are chemistry, the same chemistry we've been talking about all night, just written across continents and oceans and geological time. The carbon atom in a molecule of carbon dioxide that you just exhaled might, in a few months, be taken up by a leaf on a tree, incorporated into a sugar molecule, stored as starch, eaten by an animal, and eventually returned to the air. The atoms cycle. The chemistry continues. The rules are the same whether the system is a single cell or an entire planet. So as you drift now, let yourself feel the continuity between the small and the large, the fast and the slow, the chemical rhythms inside your cells, and the chemical rhythms of the earth. Your breathing is part of the carbon cycle. Your body heat is part of the energy flow from sun to earth to space. Your sleep is part of the circadian rhythm that has been turning for billions of years, since the first single-celled organisms evolved in an ocean lit by a young sun. You are not separate from the chemistry of the world. You are a particularly intricate expression of it, a temporary gathering of atoms that has, for a brief span, organized itself into a form that can breathe and think and drift towards sleep, held together by nothing more than the same simple rules we've been tracing all night. Giving, taking, sharing, bonds breaking and forming, energy flowing, balance maintained, and now, quiet, rest. The chemistry knows what to do. Let's turn now to something that's been waiting quietly in the background of everything we've discussed, something that connects the very small to the very large, the very fast to the very slow. This is the idea of chemical equilibrium, and it's one of those concepts that, once you see it, you start noticing it everywhere, in your body, in the air, in the oceans, in the way the whole planet balances itself. A chemical reaction, as we've seen, is a process where bonds break and new bonds form, where atoms rearrange themselves into more stable configurations. But many reactions, perhaps most of the ones that matter for living systems, do not run in only one direction. They are reversible. The products of the reaction can, under the right conditions, react with each other and reform the original starting materials. The forward reaction and the reverse reaction happen simultaneously, and when they happen at the same rate, the system reaches a state called equilibrium. At equilibrium, the amounts of reactants and products stay constant, not because the reactions have stopped, but because they are balanced, the forward and reverse processes matching each other exactly, like water flowing into a basin at the same rate it flows out. This is different from the idea that a reaction simply finishes, that all the starting material is used up and all the product is made. Many reactions never go to completion. They settle into a balance, a steady state where both sides are present in proportions that depend on the conditions, the temperature, the pressure, the concentrations. And what's crucial is that this balance can be shifted. If you add more of one reactant, the equilibrium shifts to consume it, making more product. If you remove product, the equilibrium shifts to replace it. The system responds to changes by adjusting, by moving in the direction that partially counteracts the change, a principle known as Le Chatelier's principle, after the French chemist who formulated it in the late 1800s. Your body relies on equilibrium constantly. The binding of oxygen to hemoglobin is an equilibrium process. In your lungs, where oxygen concentration is high, the equilibrium favors the binding of oxygen to hemoglobin. In your tissues, where oxygen concentration is low because your cells are constantly consuming it, the equilibrium shifts and oxygen is released. The same hemoglobin molecule, the same equilibrium reaction, picks up oxygen where it's abundant and drops it off where it's scarce, all without any conscious control, simply because the equilibrium constant responds to the local conditions. This is not a switch that someone flips. It's a balance that shifts, continuously and automatically, in response to the changing chemical environment. The pH buffer systems we talked about are equilibrium systems. The mixture of carbonic acid and bicarbonate in your blood maintains a steady pH because the equilibrium between them can absorb or release hydrogen ions as needed. Add acid and the equilibrium shifts to consume the extra hydrogen ions. Add base and it shifts to release more. The buffer is not a static thing, it's a dynamic balance, a constant back and forth that keeps the overall pH nearly constant even as your body produces acidic waste products and your diet introduces acids and bases. Equilibrium also governs the solubility of gases in your blood. The amount of oxygen that dissolves in your blood plasma depends on the partial pressure of oxygen in the air you breathe, which is why it's harder to get enough oxygen at high altitudes where the air is thinner. The amount of carbon dioxide that stays dissolved depends on the rate at which your lungs remove it, which is why holding your breath makes you feel the urge to breathe, not primarily because you need oxygen, but because carbon dioxide builds up, shifts the equilibrium, and increases the acidity of your blood, triggering the breathing reflex in your brain. The chemistry of equilibrium is what makes you feel that need for air. Let's take this idea of equilibrium and step outward, beyond your body, to the chemistry of the atmosphere. The air you breathe is not a static mixture. It's an equilibrium system on a planetary scale, with gases constantly being added and removed by different processes. Oxygen is produced by photosynthesis and consumed by respiration and combustion. Carbon dioxide is produced by respiration, combustion, and volcanic activity, and consumed by photosynthesis and by dissolving in the oceans. Methane is produced by bacteria in wetlands and by the digestive systems of animals, and consumed by reaction with oxygen in the upper atmosphere. Each of these gases exists in a dynamic, steady state, its concentration determined by the balance of sources and sinks, a balance that has shifted over geological time in response to changes in the biosphere. The story of oxygen on Earth is a particularly striking example of equilibrium on a grand scale. For the first half of Earth's history, there was almost no free oxygen in the atmosphere. The early atmosphere was dominated by nitrogen, carbon dioxide, water vapor, and methane. Then, around 2.5 billion years ago, cyanobacteria evolved the ability to perform oxygen-producing photosynthesis, and they began releasing oxygen into the oceans and the air. This was, in a sense, a pollution event, the first great environmental crisis caused by living things. Oxygen was toxic to most of the organisms that had evolved in its absence. It reacted with dissolved iron in the oceans, precipitating it out as rust, forming the banded iron formations that we mine for iron ore today. Only after the oceans and the land had absorbed all the oxygen they could, oxidizing rocks and minerals, did free oxygen begin to accumulate in the atmosphere. The equilibrium shifted, slowly, over hundreds of millions of years, from an oxygen-free atmosphere to one with enough oxygen to support the evolution of complex animal life. And the equilibrium continues to shift, even now. The carbon dioxide you exhale with every breath joins the global pool of atmospheric carbon dioxide, which has been rising for the past century and a half as humans burn fossil fuels, releasing carbon that was buried underground for millions of years. This shifts the equilibrium of the carbon cycle. More carbon dioxide in the air means more dissolves in the ocean, which lowers the ocean's pH, a process called ocean acidification, which shifts the equilibrium of carbonate minerals, making it harder for corals and shellfish to build their shells. The chemistry is straightforward, the consequences are complex, But the underlying principle is the same equilibrium we've been talking about, systems responding to changes by shifting their balance, sometimes in ways that are hard to reverse. Let's also talk about energy and equilibrium, because the two are closely connected. A chemical reaction that releases energy, an exothermic reaction, will tend to favor the formation of products, because products are at a lower energy state, more stable, more settled. But that's not the whole story. There's another factor, something called entropy, which is a measure of disorder, of the number of ways a system can be arranged. Reactions also tend to favor the side that has more disorder, more possible arrangements. A solid, with its atoms locked in place, has low entropy. A gas, with its molecules flying freely in all directions, has high entropy. When you burn wood, you're taking a solid with low entropy and turning it into gases with high entropy. The energy released drives the reaction forward, but so does the increase in disorder. The combination of these two factors, energy and entropy, determines where an equilibrium will settle. This idea, that systems tend towards states that balance energy and entropy, applies far beyond chemistry. It's a principle that runs through physics and biology, and even, some would argue, through the way complex systems of all kinds organize themselves. But here, tonight, we can keep it close to home. Your body, as an organized system, is a region of low entropy, a highly ordered arrangement of atoms in a universe that tends toward disorder. Maintaining that order requires a constant input of energy, which is why you eat, why you breathe, why your metabolism runs continuously, even while you sleep. You are, in a thermodynamic sense, a temporary pocket of order, sustained by a flow of energy, and when that flow stops, the order dissipates, the atoms scatter, the equilibrium shifts toward the simpler, more stable, less organized state. This is not a sad thing. It's simply the way the chemistry works, the way energy and entropy shape the fate of every organized system in the universe. There's a particular kind of equilibrium that's worth mentioning, one that involves not just chemical reactions but physical states. This is phase equilibrium, the balance between solid, liquid, and gas. At a given temperature and pressure, a substance will be in whatever phase minimizes its energy and maximizes its entropy. At the freezing point, solid and liquid are in equilibrium. The rate of melting equals the rate of freezing. At the boiling point, liquid and gas are in equilibrium. The rate of evaporation equals the rate of condensation. These equilibrium points depend on pressure, which is why water boils at a lower temperature at high altitudes, where the air pressure is lower, and why a pressure cooker can cook food faster by raising the boiling point of water. Your body uses phase equilibrium in a quiet but essential way. When you're too warm, you sweat. The evaporation of water from your skin takes energy, drawing heat away from your body and cooling you down. The sweat doesn't have to boil. It just has to evaporate. And evaporation happens at any temperature. It's just faster when it's warmer. The equilibrium between liquid water and water vapor shifts, and the shifting carries heat away. This is the same principle that makes a breeze feel cool on a hot day, the same principle that regulates the temperature of the entire planet through the evaporation of water from the oceans and its condensation into clouds. And then there's the equilibrium that governs the very structure of the molecules inside you. Proteins fold into their specific shapes because that folded shape represents an equilibrium between the various forces acting on the chain of amino acids. Hydrogen bonds, ionic attractions, the hydrophobic effect that pushes oily side chains toward the interior, the constraints of bond angles and distances, all of these factors balance to produce a particular three-dimensional structure, the lowest energy arrangement, the most stable fold. If you heat a protein, you add energy, and the equilibrium shifts. The protein unfolds, denatures, loses its specific shape and its function. This is what happens when you cook an egg. The proteins in the egg white unfold and tangle together, turning from clear liquid to white solid. It's also what happens during a high fever, when your body's proteins are pushed to the edge of their stability, which is why very high fevers are dangerous. The equilibrium that maintains the precise folded shapes of your enzymes and structural proteins is a delicate one, easily disrupted by changes in temperature or pH or salt concentration. Even the DNA in your cells is subject to equilibrium. The two strands of the double helix are held together by hydrogen bonds between the bases, adenine pairing with thymine, guanine pairing with cytosine. These bonds are individually weak, which is important because the strands need to be pulled apart for DNA to be copied or read. When the time comes for a cell to divide, enzymes unwind the double helix and separate the strands, and each strand serves as a template for building a new partner. The equilibrium between paired and unpaired DNA is carefully managed, shifted by proteins that bind to the DNA and stabilize one state or the other, making sure that the strands come apart when they need to and stay together when they need to. The fidelity of genetic inheritance, the passing of traits from parent to child, depends on this equilibrium, on the balance between the hydrogen bonds that hold the helix together and the cellular machinery that pulls it apart. So equilibrium is not a static, dead thing. It's a dynamic, living balance, a constant adjustment to changing conditions. It's what allows your body to maintain its internal environment despite the constant flux of the outside world. It's what allows ecosystems to persist over time as populations of different species find a balance with each other and with their resources. It's what allows the planet's climate to remain within the bounds that support life, at least over the long run, through the interplay of geological and biological processes that regulate the composition of the atmosphere and the chemistry of the oceans. Equilibrium is not the absence of change. It's the management of change, the absorption of disturbance, the return to a steady state after a perturbation. It's the chemical version of resilience, the quiet ability of systems to adjust and persist. And as you lie here in the dark, your own body is a testament to the power of equilibrium. Your temperature, your pH, your blood sugar, your ion concentrations, your hormone levels, all of these are kept within narrow ranges by networks of chemical reactions that adjust and counter-adjust, that sense deviations and correct them, that maintain the steady state that is you. This is not a fixed, unchanging state. It's a dynamic equilibrium, a constant flow of matter and energy, a constant turnover of atoms and molecules, a constant breaking and forming of bonds. You are not the same collection of atoms you were a year ago, or a month ago, or even a few days ago. Most of the atoms in your body are replaced over time, taken in through food and air and water, incorporated into your tissues, and eventually released again. The pattern persists while the material flows through. You are a shape, a process, an equilibrium, not a fixed object. And tonight, that shape is resting, that process is slowing, that equilibrium is shifting gently toward the quiet, restorative state of sleep. Let it shift, let it balance. The chemistry knows how. Let's take one final walk now, a slow one, through the quiet implications of everything we've covered, the threads that tie the different pieces together into something you can carry with you into sleep, something that doesn't require concentration or memory, just a gentle sense of what it all means. Chemistry, at its heart, is a story about connection. It's the story of how separate things become something else when they meet. An atom of sodium and an atom of chlorine, each incomplete on its own, each restless in its own way, come together and form something stable, something useful, something that seasons food and preserves life and melts snow on winter roads. Two hydrogen atoms and one oxygen atom, sharing electrons, form water, the medium in which all of life's chemistry takes place, the substance that makes up most of your body, the liquid that falls from the sky and carves canyons and fills oceans. Carbon atoms link to other carbon atoms, forming chains and rings and branching structures, and onto these carbon frameworks other atoms attach, oxygen, nitrogen, sulfur, phosphorus, and the result is the molecular machinery of life, proteins and DNA and carbohydrates and lipids, every component of every living cell. None of these connections are random. They follow rules. Rules that are simple enough to write down but rich enough to generate the entire variety of the material world. Atoms seek stable electron configurations. They give, take, or share electrons to achieve full outer shells. The patterns of giving, taking, and sharing produce the periodic relationships that Mendeleev saw in his grid of cards. The same patterns explain why water is H2O and not something else, why salt is NaCl and not something else, why carbon forms 4 bonds and oxygen forms 2 and hydrogen forms 1. The rules are consistent. They don't change from one corner of the universe to another. The sodium on Earth is the same as the sodium in a star across the galaxy. The water in your cells follows the same bonding logic as the water in a comet or a distant nebula. Chemistry is universal, a common language spoken by all matter everywhere. And yet, within these consistent rules, there is room for endless variety. The same carbon atom that forms the graphite in a pencil can, arranged differently, form the diamond in a ring. The same elements that make up a deadly poison can, arranged differently, make up a life-saving medicine. The same nitrogen that makes up most of the air you breathe can, combined with other elements in the right way, become the explosive in dynamite, or the fertilizer that feeds crops, or the protein that builds your muscles. Chemistry is not just a set of rules. It's a creative medium, a way of building an almost infinite range of structures from a finite set of pieces. And chemistry is also a story about energy, about the flow of energy through matter. Every bond that forms releases energy. Every bond that breaks absorbs energy. The balance between breaking and forming determines whether a reaction gives off heat or takes it in, whether it happens spontaneously or needs a push. Life is a way of managing this energy flow, capturing the energy released by the slow oxidation of food and using it to build and maintain the complex structures of cells and tissues. The sun pours energy onto the earth. Plants capture it through photosynthesis, storing it in chemical bonds. Animals eat plants, or eat other animals, and release that stored energy through metabolism. The energy flows, and chemistry is the riverbed through which it moves. This energy flow is never perfectly efficient. Some energy is always lost as heat, dissipated into the surroundings, increasing the disorder of the universe, even as living things maintain their own local order. This is the second law of thermodynamics, the principle that entropy, disorder, tends to increase over time. Living things are not exceptions to this law. They are temporary local reversals of the general trend, pockets of order maintained by a constant throughput of energy. When the energy stops flowing, the order dissipates, and the atoms return to simpler, more stable arrangements. This is not a tragedy, it's just the way the chemistry works. The atoms themselves are not destroyed, they are not lost. They are simply rearranged, returned to the wider pool of matter, available to be incorporated into new structures, new patterns, new life. And this brings us back to the idea of cycles, which has been a quiet theme throughout this whole journey. Atoms cycle. They move from the air to the soil, to the bodies of living things and back again. The carbon in your breath was once in the atmosphere, and before that perhaps in a leaf, and before that in the ocean, and before that in a volcanic vent, and before that in a star. The iron in your blood was forged in a stellar explosion, scattered across space, gathered into the forming earth, concentrated by geological processes, mined and smelted and forged, eaten in your food, absorbed by your intestines, incorporated into your hemoglobin, and someday, in some form, it will be released again, returned to the soil or the sea, available for other uses, other cycles, other temporary gatherings. You are not the owner of your atoms. You are their temporary steward, their brief arrangement. They were here long before you, and they will be here long after. What makes you you is not the specific atoms, which are replaced over time anyway. What makes you you is the pattern, the particular arrangement, the specific way those atoms are organized, and the specific processes they carry out. You are a pattern, a process, a verb, more than a noun. And that pattern, that process, is sustained by chemistry, by the same simple rules of giving, taking, and sharing, that govern every other material thing. There's a deep comfort in this, if you let yourself feel it. You are not separate from the natural world. You are not a stranger in a foreign universe. You are made of the same stuff as everything else, governed by the same rules, participating in the same cycles. The oxygen in your lungs was once in the lungs of countless other creatures, stretching back through evolutionary time to the first organisms that learned to use oxygen, and further back to the first cyanobacteria that learned to produce it, and further back to the geological processes that shaped the early Earth. The water in your cells has been cycling through the planet's hydrological system for billions of years, evaporating from oceans, falling as rain, flowing through rivers, percolating through soil, freezing and thawing, dissolving and precipitating, and now, for a brief moment, it's part of you. The atoms in your DNA were once in bacteria, in plants, in animals, in the soil, in the sea. They have been part of countless living things, countless temporary patterns, each one unique, each one brief, each one part of the great continuous chain of life on Earth. And now they are part of you, for this brief span of years, arranged in a pattern that can think and feel and wonder and listen to these words in the dark. And when your pattern eventually dissipates, the atoms will move on, joining other patterns, other cycles, other brief gatherings of matter into form. There is also comfort in the simplicity of the rules. The world is complicated, but the principles underneath it are not. Atoms seek stable electron configurations. They give, take, or share electrons. The resulting bonds build molecules. The molecules interact according to their shapes and charges. Energy flows, equilibrium shifts, patterns emerge, persist for a while, and dissipate. You don't need to understand every detail to appreciate the elegance of the framework, the way a few simple principles can generate the entire material richness of the world. There is comfort, too, in knowing that this understanding was hard-won, built up over centuries by thousands of careful, curious people, each one adding a piece to the puzzle. The person on the riverbank who first smelted copper, Democritus guessing at atoms with no evidence but his own reason, Jabir ibn Hayyan insisting on careful, repeatable experiments, Lavoisier weighing his sealed jars with obsessive precision, Dalton counting atoms in fixed ratios, Mendeleev laying out his cards and trusting the gaps, Thomson and Rutherford and Chadwick peering inside the atom itself. Each one asked a question. Each one looked closely. Each one added something to the picture we have now, a picture that is still being filled in, still being refined, still being extended. You are part of that story too, not as a scientist necessarily, but as a mind that can grasp these ideas, that can look at a grain of salt or a glass of water or a breath of air and see the chemistry at work. You don't need a laboratory. You don't need a degree. You just need to know that the rules are there, that the patterns are real, that the material world is not a chaos of arbitrary substances, but an orderly, interconnected system, and that you, in every moment, are part of it. So as you lie here, on the edge of sleep, let all of this settle into the background. You don't need to hold on to it. You don't need to review it or test yourself on it. The ideas will be there when you want them, and in the meantime, your body will keep doing the chemistry it knows how to do, the chemistry it has been doing since before you were born, since before your ancestors first walked upright, since before the first cells divided in the ancient sea. Oxygen will keep crossing into your blood. Iron will keep holding it and releasing it. Enzymes will keep catalyzing reactions, lowering activation energies, keeping the whole system running. Your brain will cycle through its stages of sleep, neurotransmitters rising and falling, memories consolidating, cells repairing. All of it chemistry, all of it following the same simple rules, all of it happening without your direction or attention. You are, in this moment, a resting pattern, a quiet gathering of atoms, a temporary eddy in the great flow of matter and energy. And that is enough. That is more than enough. That is everything. Let the quiet take you. Let the chemistry do its work. Let yourself drift, knowing that you are held, in every sense, by the same forces that hold the stars together, and the planets in their orbits, and the molecules in every cell. There is nothing you need to do. There is nowhere you need to go. Just rest, and let the atoms rest with you. And now, here at the end of our long walk through the history, and the ideas, and the quiet machinery of chemistry, we arrive at the simplest, most personal part of the whole story. This is the part where we stop explaining and start noticing, where we set down the names and dates and theories and simply rest in the awareness of what's happening right now, in this room, in this body, in this moment. Your breathing has slowed. Perhaps you've noticed that already, or perhaps it happened so gradually that you didn't notice at all. The air moves in and the air moves out. Each breath brings oxygen across that thin, wet membrane in your lungs, and each breath carries carbon dioxide away. This exchange has been happening since your first breath, and it will continue until your last, a rhythm that requires no thought, no effort, no attention. It is chemistry, the same chemistry we've been talking about all night, the meeting of oxygen and iron, the release of carbon dioxide from your blood, the gentle shift of equilibrium as gases move from where they're abundant to where they're scarce. Your heart is beating, a steady pulse that you can feel if you turn your attention inward, though you don't need to. With each beat, blood moves through your arteries and veins, carrying oxygen to your cells and waste products away. The heart itself is a muscle, and its contractions are driven by the same chemistry that drives every other muscle: ions moving across membranes, electrical charges shifting, proteins sliding past each other in response to chemical signals. The pacemaker cells in your heart generate their own rhythm, a chemical oscillator not so different from the circadian clock we talked about, a feedback loop of ions and channels that produces a steady beat over and over, year after year, without any conscious command from you. Your cells are repairing themselves. The wear and tear of the day, the small damages that accumulate in every living tissue, are being mended. Proteins that were damaged are being broken down and replaced. DNA that was nicked or oxidized is being repaired by specialized enzymes that patrol your genome, finding errors and fixing them. Membranes are being restored. Energy stores are being replenished. All of this is chemistry, the quiet work of maintenance that keeps a living system running, and it happens most actively while you sleep, when your body can divert energy from the demands of waking life to the essential tasks of restoration. Your brain is consolidating memories, the experiences of the day, the things you learned, the faces you saw, the conversations you had, are being processed, sorted, strengthened, or pruned. The synapses that fired together are being reinforced, their connections made stronger through the insertion of new receptor proteins. The synapses that were barely used are being weakened, their connections pruned back to make room for more important patterns. This is chemistry too, the chemistry of learning and memory, the physical reshaping of your brain's circuitry in response to experience. You are not the same person who lay down tonight. By morning, your brain will be subtly different, reorganized, refreshed, ready for a new day. And if we zoom out, beyond your body, beyond your room, the same chemistry continues everywhere. The earth turns, and the dark side of the planet, the side where you're lying right now, cools slowly, radiating the day's absorbed heat back into space. The plants in your neighborhood, if there are any, have shifted from photosynthesis to respiration, taking in oxygen and releasing carbon dioxide through the night, just as you do. The soil beneath the foundations of your building is alive with bacteria and fungi, breaking down organic matter, cycling nutrients, carrying out the slow, patient chemistry of decomposition that makes new life possible. The ocean, somewhere far away, is exchanging gases with the atmosphere, absorbing carbon dioxide, releasing oxygen, its chemistry shifting with the temperature and the seasons, and the slow accumulation of changes that humans have set in motion. All of it is connected. The oxygen you're breathing right now might have been produced by a phytoplankton in the Pacific Ocean a few weeks ago, or by a tree in a forest 1,000 miles away, or by a blade of grass in a field you've never seen. The carbon in your exhaled breath might be taken up by a leaf tomorrow, or dissolve in a raindrop, or drift across a continent before settling into the sea. The atoms that make up your body have been part of rocks and water and air and other living things, and they will be again. You are a temporary arrangement, a brief gathering, a pattern that persists for a while and then disperses, leaving the atoms to continue their long journey through the cycles of the earth. There is no separation. There is no barrier between the chemistry inside you and the chemistry outside you. The membrane of your lungs is a boundary, but it's a boundary designed to be crossed, a border that oxygen and carbon dioxide pass through constantly, a place of exchange rather than isolation. The lining of your gut is a boundary, but it's a boundary designed to let nutrients through, to absorb the breakdown products of your food and pass them into your bloodstream. Your skin is a boundary, but even that boundary is porous, letting water out as sweat, letting heat out to cool you, letting in the touch of the sheets and the coolness of the night air. You are an open system, constantly exchanging matter and energy with your surroundings, and that openness is what keeps you alive. So as you lie here, on the very edge of sleep, let yourself feel that openness. Let yourself feel the continuity between your body and the room, between the room and the world outside, between the world and the vast universe of stars and planets and drifting atoms from which you came. You are not an isolated self, a mind trapped in a body, a lonely consciousness adrift in an indifferent cosmos. You are a particular expression of the same chemistry that governs everything, a pattern that the universe has formed, for a little while, in this particular place and time. The atoms that make you up have been following the same rules since they were forged in ancient stars. The forces that hold you together are the same forces that hold together every grain of salt and every drop of water, and every molecule in every cell of every living thing. You belong here. You are part of this. You always have been. And now, as sleep comes closer, as the words begin to fade into the background, there is nothing more you need to understand. The understanding has been offered. It will be here if you want to return to it. But right now, in this moment, understanding is less important than resting. Let the ideas settle where they will. Let the chemistry do what it knows how to do. Let your breathing find its own rhythm, your heart its own beat, your brain its own slow cycles of restoration and repair. You don't need to manage any of it. You never did. The chemistry has been running this whole time, and it will keep running, tonight and tomorrow and for all the nights and days of your life, without your supervision, without your effort, without your awareness. So let go. Let the pillow take the weight of your head. Let the mattress support the length of your body. Let your muscles soften, your jaw unclench, your shoulders drop. Let your thoughts drift where they will, without trying to steer them or hold them or make sense of them. They are just electrical patterns, chemical signals, the chatter of a brain that is slowly powering down for the night. They don't need your attention. They don't need your engagement. Let them come and let them go, like clouds crossing a dark sky, like ripples spreading across still water, like the slow drift of atoms from one temporary arrangement to another. The chemistry will continue. The oxygen will keep crossing into your blood. The iron will keep holding it and releasing it. The enzymes will keep catalyzing their reactions, thousands per second in every cell. The DNA will keep being repaired. The memories will keep being consolidated. The circadian clock will keep ticking, marking the passage of the night, preparing your body for the morning that will come in its own time. None of this needs you. All of this is you. You are the chemistry, and the chemistry is resting, settling, finding its equilibrium, moving gently toward whatever arrangement is most stable, most settled, most at rest. And somewhere above you, if you could see through the ceiling and the roof and the atmosphere, the stars are shining, the same stars whose deaths forged the atoms that make up your body. The light that left those stars millions or billions of years ago is traveling through space, and some of it is falling on the Earth, on the side that's facing away from the sun, on the dark half of the planet where you lie sleeping. The same nuclear reactions that built the elements are still running in the cores of stars, fusing hydrogen into helium, helium into carbon and oxygen, building the heavier elements that will someday, when those stars die, be scattered into space to form new planets, new oceans, new life, new temporary gatherings of matter into patterns that can think and feel and wonder. You are part of that story, the story of matter organizing itself into ever more complex forms, following simple rules, giving, taking, sharing, always moving toward stability, always seeking the full outer shell, the settled state, the quiet completion. And tonight, that story pauses, here, in this room, in this body, in this moment of rest. The universe has made a shape called you, and for a little while, that shape gets to lie in the dark, and breathe and drift towards sleep, held by the same forces that hold the galaxies together, sustained by the same chemistry that powers the stars. That is enough. That is more than enough. That is everything. So sleep now. Let the quiet take you. Let the darkness hold you. Let the chemistry run its course. You are exactly where you need to be, made of exactly what you need to be made of, doing exactly what you need to be doing. There is nothing to achieve, nothing to prove, nothing to figure out. There is only rest, and the steady, quiet, ancient rhythm of atoms arranging and rearranging, bonds forming and breaking, energy flowing, life continuing, all through the night, all without your effort, all without your worry. Good night. Sleep well. The chemistry has you. It always has. It always will.